Hello, and welcome to the Sleepy Astronomer. Tonight, we're going to explore something that shouldn't exist, a region of space so empty, so impossibly vast, that when astronomers first discovered it, they thought their instruments had failed. They checked their telescopes, they recalibrated their equipment, they observed the same region again, expecting to find the galaxies that had to be there. But there was nothing, just darkness, just silence, just an enormous spherical void where thousands of galaxies should have been shining. That void is real. It's called the Boötes Void, and it's one of the strangest structures in the observable universe, a bubble of almost nothing. Roughly 330 million light-years across, sitting in a cosmos that's supposed to be full of galaxies, full of structure, full of light. For more than 40 years, astronomers have studied it, mapped it, tried to understand how something so profoundly empty could exist in a universe so full of matter. And the more we learn about it, the stranger it becomes. If you're settling in for the first time, welcome aboard this journey into cosmic mystery. And if you've travelled with me before through galactic collisions and stellar neighbourhoods, it's wonderful to have you back among the stars. Tonight's journey is different, a detective story that begins with confusion, traces through decades of investigation, and ends not with simple answers, but with deeper questions about what emptiness really means. Wherever you are tonight, settling in for rest or simply curious about the invisible architecture of the cosmos, I'm so glad you're here. If this journey into the void helps you unwind or fills you with that particular kind of wonder that comes from discovering the universe is stranger than we imagined, feel free to give the video a like. And if you'd like to help other space enthusiasts discover these peaceful astronomical journeys, a subscription really does help the channel reach fellow dreamers looking for calming content to drift off to. It means the universe to me, and it helps build this wonderful community of curious minds and starlight admirers. So, find your most comfortable position and let's begin, because tonight we're going to follow astronomers into a mystery that started with a simple survey in 1981 and ended with the realization that the universe isn't quite as full as we thought it was, that there are places where light simply vanishes, where galaxies refuse to form, where the cosmic web has holes large enough to swallow everything we can see. The story starts, as many astronomical stories do, with someone noticing something wrong. In this case, it was 1981, and a team of astronomers, Robert Kirshner, Augustus Oemler Jr., Paul Schechter, and Stephen Schechtman, were conducting what seemed like routine work. They were mapping galaxies in 3 dimensions, using a technique called redshift measurement to determine not just where galaxies appeared in the sky, but how far away they were. It was painstaking work, requiring night after night at the telescope, spectrum after spectrum, building up a 3-dimensional picture of the universe one galaxy at a time. Their target region was in the constellation Boötes, a relatively unremarkable patch of sky between Ursa Major and Virgo. Based on what they knew about galaxy distributions, based on decades of sky surveys and statistical studies, they expected to find about 2,000 galaxies in that volume of space. That's what the numbers predicted. That's what the universe should contain, given average galaxy densities and the size of the region they were studying. Instead, they found 8. Not 800, not 80. 8 galaxies, scattered across a volume that should have contained thousands. And the more they looked, the more they reobserved, the more they checked their work, the clearer it became. The emptiness was real. They weren't missing galaxies because of instrumental problems or bad weather or unfortunate timing. The galaxies simply weren't there. What they'd discovered was a void, a vast bubble in the cosmic structure where galaxies were extraordinarily rare, where the normal density of matter was reduced to a tiny fraction of what it should be, where space itself seemed to have forgotten how to make galaxies, it wasn't just an empty region, it was impossibly empty, statistically anomalous, far larger and far more underdense than anything the prevailing theories predicted should exist. Now here's the thing about space. It's not supposed to be that empty. Not anymore. Not after nearly 14 billion years of cosmic evolution, of gravity pulling matter together, of structure growing from the tiny quantum fluctuations in the early universe. Space has patterns, structure, organization. Galaxies cluster together along vast filaments and sheets, creating what we call the cosmic web, a beautiful, intricate network of matter threading through the universe, with galaxies strung along like lights on a three-dimensional spider's web. But where there's structure, there are also voids, the spaces between the filaments, the bubbles within the web. That's normal. That's expected. Voids are part of how the universe organizes itself, the natural consequence of matter, flowing toward regions that were slightly more dense in the beginning and leaving behind regions that were slightly less dense. Every void has a story about gravity and structure formation, about matter flowing away toward denser regions, about the universe sorting itself over billions of years. But the Boötes Void isn't normal. It's too large, too empty. It sits right at the edge of what should be statistically possible, a bubble so enormous and so underdense that its very existence challenges our understanding of how structure forms. It's not just that galaxies are rare inside it, it's that they're almost absent, reduced to a tiny fraction of normal density, roughly 3% of what you'd expect. 3%. That's not a small discrepancy. That's not measurement error or sampling bias. That's a genuine anomaly, something that demands explanation, something that tells us the universe can do things we didn't think were possible. And here's what makes it fascinating rather than merely puzzling. We can study it. We can map its boundaries, trace its shape, count the few galaxies that do exist inside it, measure its properties in extraordinary detail. The void isn't hiding, it's right there, enormous and obvious once you know how to look for it, about 700 million light-years away from Earth in the direction of Boötes. Close enough to study, large enough to matter, strange enough to keep astronomers arguing about it for more than 40 years. Tonight, we're going to follow that investigation from beginning to wherever it leads. We'll trace the discovery, understand the scale, explore the theories about how it formed and why it's so empty. We'll meet the few ghost galaxies that somehow survive inside it, isolated and strange. We'll stand at the void's edge and wonder what it means when something so large contains so little. And we'll discover that nothing isn't quite as simple as it sounds, that even the emptiest place in the observable universe is still full of quantum fields and dark energy and subtle gravitational currents. This is a story about emptiness, about absence, about the spaces between things that turn out to be just as important as the things themselves. It's a story that begins with confusion and builds through investigation towards something like understanding, though perhaps not the kind of understanding that comes with simple answers. Because here's the truth about the Boötes Void. We know it's there. We've mapped it, measured it, studied it for decades. We understand how voids form in general, how gravity sorts matter and leaves empty spaces behind. But we still don't fully understand why this void is so extreme, so anomalous, so profoundly empty compared to everything else we observe. The mystery hasn't been completely solved, and maybe that's appropriate. Maybe some mysteries are meant to remain mysterious, not because we lack the tools to study them, but because they reveal something fundamental about how the universe works, or doesn't work, in ways we're still learning to comprehend. So, settle in, get comfortable, and let's begin our gentle journey into one of the universe's strangest structures, the place where light vanishes, where galaxies refuse to form, where the cosmic web has a hole large enough to swallow our entire understanding of how structure should behave. Let's discover together what it means when nothing becomes something worth studying, when absence becomes a presence in its own right, when emptiness teaches us more about the universe than all the matter and light combined. The void is waiting, and despite containing almost nothing, it has quite a story to tell. Let's talk about how astronomers spend their nights, because it's not quite what you might imagine. There's a certain romance to the idea, standing at a telescope under dark skies, gazing up at the cosmos, making discoveries that change our understanding of the universe. And that happens, certainly, but most of astronomy is considerably less poetic. Most of astronomy is data collection, night after night of pointing telescopes at specific coordinates, taking spectra, recording numbers, building up catalogues that might not reveal their secrets for months or years after the observations are complete. In 1981, Robert Kirshner, Augustus Oehmler Jr., Paul Schechter, and Stephen Schechtman were in the middle of exactly that kind of work. They were conducting what's now called the CFA Redshift Survey, CFA standing for the Center for Astrophysics at Harvard, though the observations were being done at various telescopes, including ones in Arizona and Chile. Their goal was straightforward enough to state but extraordinarily tedious to execute. Map the three-dimensional positions of galaxies in large volumes of space. Now, mapping galaxies sounds simple until you remember that when you look at the night sky, you're looking at a two-dimensional projection of a three-dimensional universe. You can see where galaxies are on the celestial sphere, their coordinates in right ascension and declination, the cosmic equivalent of longitude and latitude, but that doesn't tell you how far away they are. A galaxy that appears next to another galaxy in the sky might be twice as far away, or 10 times, or 100 times. Without distance information, you're trying to build a three-dimensional map using only 2 dimensions of data. It's like trying to understand the layout of a city by looking at a photograph. You can see which buildings are next to which, but you have no idea whether one building is a block away or a mile away. The breakthrough that made three-dimensional mapping possible was redshift. When you take the spectrum of a galaxy, spreading its light out into a rainbow of colors, and measuring the brightness at each wavelength, you can identify specific spectral lines, patterns created by elements like hydrogen and helium, and oxygen absorbing or emitting light at very specific wavelengths. Those spectral lines are like fingerprints. We know exactly where they should be in the spectrum based on laboratory measurements here on Earth. But when you look at the spectrum of a distant galaxy, those spectral lines have shifted. They're not quite where they should be. The technical reason involves the expansion of space itself. Space is getting bigger, stretching like a balloon being inflated, and that stretching causes the wavelengths of light to stretch along with it. Light that left a galaxy millions of years ago arrives at Earth with longer wavelengths than when it started, shifted toward the red end of the spectrum, hence redshift. And here's the beautiful part. The amount of redshift tells you the distance. The farther away a galaxy is, the more space has expanded during the light's journey, the more the wavelengths have stretched, the larger the redshift. It's not a perfect ruler. There are complications and corrections and subtleties that can trip you up, but it works. Measure the redshift, calculate the distance, plot the galaxy's position in 3 dimensions. Do this for hundreds or thousands of galaxies, and you start to see structure emerge. The cosmic web reveals itself, one spectrum at a time. This is what Kirshner and his colleagues were doing. They'd chosen several regions of sky to survey, and one of those regions happened to be in the constellation Boötes. It was a good target, far enough from the plane of the Milky Way that you weren't looking through too much dust and gas from our own galaxy, positioned where it would be visible from Northern Hemisphere observatories, large enough to contain a statistically meaningful number of galaxies. Based on previous sky surveys, based on what astronomers knew about average galaxy densities in the universe, they expected to find about 2,000 galaxies in the volume of space they were surveying. That was the prediction. That was what the statistics said should be there. And so they started observing, pointing their telescopes at galaxy after galaxy, taking spectra, measuring redshifts, slowly building up the three-dimensional map. And then something strange started happening, or rather, something strange started not happening. The first few observations came back as expected. Galaxies appeared, their spectra showed the characteristic patterns of stellar light, redshifts were measured, distances calculated. The map started to populate with points representing galaxies, scattered through three-dimensional space. Everything normal, everything proceeding according to plan. But as they continued observing, as they moved their telescope to new targets in the same region, the galaxies stopped appearing. Not gradually, not with some obvious pattern to explain why certain areas were empty. They just weren't there. Target after target came back with no galaxy detected, or with a galaxy so faint it was barely above the detection threshold, or with obvious problems that meant the observation needed to be retried. Now this happens sometimes in astronomy. Equipment fails, weather interferes, cosmic rays hit your detector at the wrong moment and ruin the data. You get clouds you didn't expect, or your spectrograph develops a problem, or the pointing of the telescope is slightly off, and you're not looking exactly where you think you're looking. These are frustrating but normal parts of observational astronomy. You check your equipment, you reobserve, you try again. So that's what they did. They checked the telescopes. Everything seemed fine, the mirrors were clean, the tracking was accurate, the spectrographs were functioning normally. They checked their target lists, the coordinates were correct, they checked the weather logs. The nights had been clear, the seeing conditions reasonable, nothing obviously wrong. They reobserved some of the empty positions, thinking maybe they'd just had bad luck the first time through, and they got the same result, no galaxies, or occasionally a galaxy, but far fewer than should have been there. The emptiness persisted, the absence remained. And gradually, as more data accumulated, as they observed more and more positions in this region and found the same inexplicable lack of galaxies, a different kind of realization started to set in. This wasn't instrumental failure. This wasn't bad weather or bad luck. The galaxies weren't missing because of problems with their observations. The galaxies were missing because they weren't there. The emptiness was real. This is the moment in every scientific investigation where confusion turns into something more interesting, where the problem stops being, why isn't our equipment working, and becomes, why is the universe behaving in a way we didn't expect? It's uncomfortable, that transition. It means your assumptions were wrong. It means the universe is stranger than you thought, but it's also exhilarating, because it means you might have found something genuinely new, something that doesn't fit into the neat categories you'd constructed. So they did what any good scientist would do. They kept observing. They expanded their survey, observed more targets, built up more data, and they started plotting the results not just as a list of galaxies and distances, but as an actual three-dimensional map, with each galaxy represented as a point in space, distributed according to its measured position and distance. That's when the bubble revealed itself. When you plot galaxies in 3 dimensions, when you look at their distribution through space, rather than just projected onto the sky, structure emerges. You see filaments where galaxies cluster together along lines. You see walls and sheets where galaxies form 2-dimensional surfaces. You see nodes where multiple filaments intersect, creating dense concentrations that we call galaxy clusters. And you see voids, empty spaces between the structures, bubbles where galaxies are rare or absent. This is the cosmic web, and it's beautiful in its own way. The universe organizes matter into this intricate 3-dimensional tapestry, this network of structure with voids between. But the voids are supposed to be relatively small. They're supposed to have some galaxies in them, just fewer than in the filaments and walls. They're supposed to fit within the predictions of how structure forms. The void in Boötes didn't fit those predictions. As Kirshner and his colleagues plotted their data, as they watched the 3-dimensional distribution take shape, it became clear that they'd discovered something extraordinary. There was an enormous spherical region, roughly 330 million light-years in diameter, where galaxies were almost completely absent. Not just sparse, not just underdense, almost entirely empty. Where 2,000 galaxies should have been, they'd found 8. Later surveys would find more, pushing the count up to around 60 galaxies total. But that's still only about 3% of what should be there. 3%. The void's boundaries weren't perfectly sharp. Voids never are, because the universe doesn't work with clean edges. But the center was unmistakable. There was a core region where galaxy density dropped to nearly 0, and that region was gigantic, far larger than any void that had been discovered before, far emptier than the models predicted should be possible, an anomaly, a statistical outlier, a hole in the cosmic web large enough that you could fit thousands of Milky Way-sized galaxies inside it, if only there were galaxies there to fit. They published their findings, and the astronomical community reacted with, let's say, healthy skepticism. Not disbelief exactly. The data was solid, the observations were careful, and Kirshner's team had a good reputation. But surprise, confusion, a certain amount of, that can't be right, can it? Because voids that large, that empty, weren't supposed to exist. The lambda CDM model, our best understanding of how the universe evolves, how structure forms from tiny density fluctuations in the early universe, predicts that voids should exist, yes. Gravity pulls matter together in overdense regions, leaving underdense regions behind. That's normal. That's expected. But the size and emptiness of the Boötes Void pushed right up against the edge of what the model could comfortably explain. It wasn't impossible, technically, just unlikely, very unlikely. The kind of unlikely that makes you wonder if maybe there's something about structure formation that we don't fully understand. Other astronomers started observing the same region, confirming the results. They found the void too. They measured its size and its galaxy deficit, and got similar numbers. And as more sensitive surveys were conducted over the following decades, as telescopes improved and detection methods became more sophisticated, the basic picture held up. The Boötes Void was real. It was enormous. It was profoundly empty. And it wasn't the only one. Other large voids were discovered in subsequent surveys, proving that while Boötes was extreme, it wasn't unique. The universe makes these things. The cosmic web has holes. That's just how structure works, apparently. But Boötes remained special. Even among other large voids, Even as the catalogue of known voids grew into hundreds and then thousands of entries, Boötes stood out, largest and emptiest of the large voids. The most extreme example of a phenomenon that was already surprising. The void that started it all, the first one dramatic enough to really force astronomers to confront the fact that empty space could be emptier than anyone had imagined. And here's what makes this discovery particularly fascinating from a historical perspective. It happened because of patient, systematic work, not through some brilliant insight or revolutionary new theory, not through a dramatic telescope observation that changed everything in an instant, just through the slow, methodical process of mapping the universe one galaxy at a time, building up a three-dimensional picture through hundreds of nights at the telescope, analyzing data carefully, and being willing to trust the results even when they didn't make sense. Science often works this way. The big discoveries don't always come from genius breakthroughs. Sometimes they come from doing the work, from being thorough, from mapping what's actually there rather than what you expect to find. Kirshner and his colleagues weren't looking for a void. They were just trying to build a galaxy catalogue, trying to understand large-scale structure, trying to map the cosmic web. And in the process of doing that careful, systematic work, they stumbled into one of the strangest structures in the observable universe. Now, before we move forward into understanding what this void actually is and how it formed, we should take a moment to appreciate what discovering extreme emptiness meant in a broader human context. Because humans have always had complicated relationships with voids, with absence, with nothingness. The idea of something that's not there, that's defined by what it lacks rather than what it contains, pushes against our intuitions in uncomfortable ways. Ancient cultures across the world had myths about primordial emptiness, about the void that existed before creation. The Greeks called it chaos, not chaos in the sense of disorder, but chaos as the initial state, the gap or void that preceded everything else. In the beginning, according to Hesiod's cosmogony, there was chaos, and then came Earth and Tartarus and Eros. Chaos first, the void before the substance. Norse mythology had Ginnungagap, the yawning void between Niflheim, the world of ice, and Muspelheim, the world of fire. In that gap, in that emptiness, the first beings emerged when ice and fire met and mingled. The void wasn't empty in the sense of being meaningless. It was pregnant with potential, the necessary space where creation could happen. Egyptian creation myths spoke of Nu or Nun, the primordial waters, the formless expanse that existed before the ordered world emerged. Not quite a void, but an undifferentiated emptiness, a state of non-being that preceded being. Even in relatively modern times, on old maps from the age of exploration, cartographers would mark unexplored regions with warnings. Here be dragons. The unknown spaces, the parts of the map that were empty not because nothing existed there, but because we hadn't looked yet, carried a special kind of menace. The void as threat, the absence as danger. This fear of emptiness has a name in philosophy and art history. Horror vacui, the fear of empty space. Medieval manuscripts were often densely decorated, every inch of parchment covered with text or illumination or intricate marginalia, as if leaving blank space would be somehow wrong, somehow threatening. Nature abhors a vacuum, we say, attributing to nature our own discomfort with absence. And yet philosophy has also recognized the necessity of emptiness. The French mathematician and philosopher Blaise Pascal wrote about the terror of infinite empty spaces. The eternal silence of these infinite spaces frightens me. He was thinking about the void of space itself, the enormous distances between stars, the realization that most of the universe is empty and silent and utterly indifferent to human existence. That same recognition, That emptiness can be profound, even sublime, runs through certain philosophical and spiritual traditions. Buddhist philosophy talks about shunyata, often translated as emptiness or voidness, but not meaning nothingness in a nihilistic sense. It means something more like the absence of inherent, independent existence, the recognition that things don't have fixed, permanent essences, but arise in relationship to everything else. Emptiness in Buddhist thought isn't terror, it's liberation from false ideas of permanence and self. Taoism speaks of Wu, non-being, and celebrates the usefulness of emptiness. The Tao Te Ching contains a famous passage. 30 spokes converge at the hub, but it's the emptiness that makes the wheel useful. We shape clay into a pot, but it's the emptiness inside that holds whatever we want. These are all human attempts to grapple with absence, to make sense of nothingness, to understand what it means when something isn't there. And astronomers in 1981, staring at their three-dimensional maps and seeing an enormous bubble where galaxies should have been, were confronting their own version of that ancient philosophical puzzle. What does it mean when space is emptier than it should be? What do you do with a void that's too large, too empty, too strange to fit comfortably into your models? There's also something sublime about it, in the technical, philosophical sense. Edmund Burke, writing in 1757 about aesthetics, distinguished between the beautiful and the sublime. Beautiful things are harmonious, well-proportioned, gentle. Sublime things are vast, powerful, even terrifying, but in a way that draws you toward them rather than repelling you. The sublime is terror mixed with awe, the feeling you get standing at the edge of a cliff or watching a thunderstorm or contemplating something so large it defeats your ability to comprehend it. The Boötes Void is sublime. It's too large to visualize properly. 330 million light-years. You can say the number, you can write it down, you can even do calculations with it. But you can't really imagine it. Your brain doesn't have the capacity to make that distance feel real, and that failure to comprehend, that inability to make the void fit into your mental categories, is part of what makes it fascinating. It's beautiful because it's terrible. It's compelling because it's incomprehensible. Immanuel Kant, building on Burke's ideas, talked about the mathematical sublime, the feeling you get when confronted with quantities so large they defeat imagination. The void offers exactly that. You can understand intellectually that it's enormous. You can compare it to other large things and recognize that it's bigger than those, but you can't hold it in your mind as a lived experience. The understanding remains abstract, intellectual, divorced from feeling. And perhaps that's appropriate. Perhaps voids are meant to remain somewhat mysterious, somewhat beyond our comfortable grasp. Not because we lack the tools to study them. We can map them, measure them, understand them scientifically with great precision, but because they represent something fundamental about how the universe works that doesn't map neatly onto human intuitions about how things should be. The Boötes Void wasn't the first emptiness humanity had discovered, but it was the first one we could measure, map, and study in detail. The first one where we could say with confidence, here is a place where galaxies aren't, where matter is absent, where the cosmic web has a hole large enough to fit thousands of galaxies, if only there were galaxies to put there. In that sense, discovering the void was an act of courage, choosing to look directly at absence, to study nothing, to take the emptiness seriously, rather than dismissing it as instrumental error or bad luck. And what Kirshner and his colleagues discovered that night, as they plotted their data and watched the bubble emerge, was that the universe is stranger than we thought. Not just in the sense of containing exotic objects or unusual phenomena, though it certainly does that, but strange in its structure, in its architecture, in the way it organizes matter and leaves enormous empty spaces behind. The void was a revelation, not about what the universe contains, but about what it doesn't contain, about how absence can be just as important as presence, about how nothing can tell us as much as something if we're willing to look carefully enough. In the years since that discovery, astronomers have found hundreds of other voids. They've built up catalogues, developed theories, run simulations to understand how voids form and evolve. The Boötes Void is no longer unique. It's part of a population, the most extreme member of a class of structures that we now recognize as fundamental to how the universe organizes itself. We understand voids much better than we did in 1981, but understanding doesn't always diminish mystery. Sometimes it deepens it. Sometimes the more you learn about something, the stranger it becomes. And the Boötes Void, even after decades of study, remains profoundly strange. Larger than it should be, emptier than predictions suggest. A bubble in the cosmic foam that pushes right up against the edge of what our theories can comfortably explain. It's still there, of course, still enormous, still empty, still quietly challenging our understanding of how structure forms and why certain regions of space remain so profoundly underpopulated. Roughly 700 million light-years away, in the direction of the constellation Boötes, there's a place where light vanishes, where galaxies refuse to form, where the universe demonstrates that it can create absence as easily as it creates presence. And that's where our journey really begins, not with the discovery itself, but with understanding what that discovery means. What is this void? How large is it really, in ways we can actually comprehend? How did it form? Why is it so empty? And what can it teach us about the universe and about the strange relationship between something and nothing, between presence and absence, between the cosmic web and the holes within it? Those are the questions we'll explore together. But first, before we can understand the void, we need to appreciate its scale. We need to find ways to make 330 million light-years feel real, or at least feel like more than just a number. We need to zoom out from human perspective and try to grasp just how enormous this bubble of almost nothing really is. That's where we're heading next, into the incomprehensible scale of cosmic emptiness and the strange ways we try to make the unmeasurable feel knowable. Let's try to understand how big 330 million light-years actually is, because saying the number is one thing, and comprehending it is quite another. The human brain evolved to understand distances you can walk in a day, maybe distances you can see from a hilltop. It did not evolve to make sense of cosmic distances measured in millions of light-years. So we're going to need to build up to this gradually, starting from scales we can actually grasp and working our way out until we hit the point where comprehension breaks down entirely. We'll begin with something comfortable, Earth. Our planet has a diameter of about 12,742 kilometers, or if you prefer, roughly 7,918 miles. That's a distance you can kind of hold in your mind. If you could somehow walk around Earth's equator, which you can't, obviously, because there are oceans and mountains and property rights. But if you could, and if you maintained a steady walking pace of about 5 kilometers per hour, it would take you about 106 days of continuous walking. Exhausting, certainly, but imaginable. You could tell a story that spans 106 days. You could follow someone on that journey. Now let's zoom out to the solar system. The distance from the Sun to Neptune, the outermost planet since we rather rudely demoted Pluto, is about 4.5 billion kilometers. That's getting harder to visualize, but we can still find analogies. If you could somehow drive a car to Neptune at highway speeds, maintaining 100 kilometers per hour constantly, it would take you about 5,100 years. That's longer than recorded human history. That's farther in time than the earliest Egyptian pyramids. The scale is starting to slip away from comfortable human experience, but you can still sort of grasp it through the analogy. Next step, the nearest star. Proxima Centauri, our closest stellar neighbour, sits about 4.24 light-years away. A light-year is the distance light travels in 1 year, moving at 300,000 kilometers per second, a speed so fast that light could circle Earth's equator more than 7 times in a single second. At that speed, light from the Sun takes about 8 minutes to reach Earth. Light from Proxima Centauri takes 4.24 years. If you somehow found a spacecraft that could travel at 1% of the speed of light, which would be an extraordinary technological achievement, the journey to Proxima Centauri would take 424 years. Multiple generations would be born, live their entire lives, and die during that journey. The scale has now completely exceeded anything we can experience directly. But we're not even close to galactic scales yet. Let's keep going. Our Milky Way galaxy stretches somewhere between 100,000 and 200,000 light-years, from edge to edge, depending on exactly where you decide the edge is. Galaxy boundaries are fuzzy things, as we've discussed before. Light that left one edge of the Milky Way travelling at the universe's speed limit would take 100,000 years or more to reach the other edge. Modern humans as a species are only about 300,000 years old. The Milky Way is smaller in time than our species' history, but not by much. You could almost map human evolution onto a journey across the galaxy, if you were being poetic about it. The local group, our gravitational neighbourhood, the small cluster of galaxies including the Milky Way, Andromeda, and about 50 smaller galaxies, spans roughly 10 million light-years. We're now solidly beyond any human frame of reference. There are no useful analogies anymore. We can only work with numbers, with mathematical relationships, with abstract comparisons that don't really make the distance feel real, because it can't feel real to a brain built for walking distances. The Virgo supercluster, the larger structure that our local group is part of, stretches about 110 million light-years across. It contains thousands of galaxies arranged in clusters and groups, all loosely bound together by gravity, all part of one enormous cosmic structure. And here's where we finally arrive at our destination. The Boötes Void, at 330 million light-years in diameter, is roughly 3 times the size of the Virgo supercluster. It's a bubble of almost nothing large enough to contain 3 entire superclusters, if only there were superclusters there to contain. Let's try to contextualize this through volume, because maybe that will help, though honestly it probably won't. The Boötes Void has a volume of approximately 236 million cubic megaparsecs. A megaparsec is about 3.26 million light-years, which is already a distance that defeats comprehension, and we're cubing it and then multiplying by 236 million. The numbers stop meaning anything. They're just sounds we make, arrangements of digits that represent quantities our brains can't process as experiential reality. Here's another way to think about it. Based on average galaxy densities in the universe, that volume should contain about 2,000 Milky Way-sized galaxies. 2,000 entire galaxies, each one containing hundreds of billions of stars, each star potentially hosting planets, each galaxy representing everything we can see when we look up at the night sky, and then multiplied by 2,000. That's what should be in that volume of space, based on how matter is typically distributed. Instead, it contains approximately 60 galaxies. That's 3% of expected density. Imagine expecting to meet 2,000 people at an event and finding 60. Imagine a city that should have 2,000 buildings but has 60. Imagine any context where you expect something to be full and it's 97% empty. That's the Boötes Void. That's the scale of absence we're dealing with. Other voids exist, and we've found many of them since 1981. They're normal parts of cosmic structure, the bubbles in the cosmic foam, the spaces between the filaments where galaxies cluster. Most voids have densities around 10 to 20% of average. They're underdense, but not empty. They have some galaxies, just fewer than you'd find in the filaments and walls. That's expected. That's what structure formation predicts. Gravity pulls matter together in some regions, leaving other regions relatively empty. The voids are the relatively empty regions. But Boötes is different. 3% density isn't relatively empty. It's profoundly, almost absurdly empty. It's the most underdense large void we've found. Other voids might be larger in certain dimensions, or might have interesting properties of their own. But Boötes combines size and emptiness in ways that make it stand out, even among other extreme voids. It's the void that defines what voids can be at their most extreme. Now let's try some visualization exercises, because maybe if we can imagine the void in different contexts, it will help make the scale feel more real. Though I should warn you, this probably won't work because the scale is fundamentally incomprehensible, but we can try. Imagine if the Boötes Void were placed near Earth, centered somewhere nearby in space. How much of the sky would it cover from our perspective? Well, at 330 million light-years across and placed, say, 700 million light-years away, which is roughly where the actual void sits, it would span about 27 degrees of arc across the sky. For comparison, the full moon spans about half a degree. The void would be roughly 54 times wider than the full moon appears. It would dominate whatever region of sky it occupied, stretching from horizon to zenith if you were unlucky enough to be looking in its direction at the wrong time. You couldn't miss it. Or rather, you couldn't miss the absence of galaxies where galaxies should be visible. Here's another comparison that might help. If you could somehow travel at the speed of light, which you can't because physics doesn't allow massive objects to reach light speed, but let's pretend, how long would it take to cross the void? At 330 million light-years across, moving at light speed, the journey would take 330 million years. For reference, 330 million years ago on Earth, we were in the Carboniferous period. The earliest reptiles were just beginning to appear. Amphibians dominated the landscape. The supercontinent Pangaea hadn't formed yet. Trees had only recently evolved, and forests were spreading across the continents for the first time in Earth's history. If you'd somehow started crossing the void at light speed back then, and maintained that speed constantly through all those millions of years of geological time, through the rise of dinosaurs and their extinction, through the evolution of mammals and then primates and then humans, through all of recorded human history and beyond, you'd arrive at the other side approximately now. The crossing would span the entire time, from the first reptiles to the present moment. That's how large the void is. And if you tried to cross it at spacecraft speeds, let's say you had some hypothetical spacecraft that could manage 1% of light speed, which would be a remarkable achievement, the journey would take 33 billion years. The universe itself is only 13.8 billion years old. You'd need more than 2 complete lifetimes of the universe to cross the void at that speed. By the time you reach the other side, assuming the universe's expansion doesn't tear things apart first, all the stars would have died, all the black holes would have evaporated through Hawking radiation, and space would be cold, dark, and essentially empty everywhere. The void would have outlasted everything. These comparisons don't really help, do they? They're just different ways of saying unimaginably large, different frameworks for the same basic incomprehension. And perhaps that's the point. Perhaps the void is teaching us something about the limits of human understanding, about how our brains simply aren't equipped to make sense of certain scales. Let's try one more angle, the loneliness factor. Imagine for a moment that you're somehow observing the universe from a planet orbiting a star in one of the 60 galaxies inside the Boötes Void. What would the night sky look like? Here on Earth, when we look up at the night sky from a dark location, we see thousands of stars, all of them in our own Milky Way, members of our galactic family. We see the Milky Way's band stretched across the sky, that river of faint light created by millions of distant stars in our galaxy's disk. If we have a telescope, even a small one, we can see other galaxies. Andromeda is visible to the naked eye as a faint smudge. With larger telescopes, we can see hundreds or thousands of galaxies, evidence that we live in a universe full of structure, full of light, full of cosmic activity. From inside the Boötes Void, the sky would be different, profoundly different. You'd still see stars if your planet orbited a star, if your galaxy had stars. You'd see the other stars in your galaxy just fine. But when you looked beyond your galaxy, beyond your local stellar neighborhood, you'd see almost nothing. The nearest galaxy might be millions or tens of millions of light years away. Even with powerful telescopes, the sky would be mostly dark. No rich field of galaxies, no cosmic web visible in the background. Just darkness, isolation, the profound emptiness of being stranded in the most underdense region of space. And here's the disturbing thought. If humans had somehow evolved in a galaxy inside the Boötes Void, our astronomy would have developed very differently. We might not have discovered that the universe contains billions of galaxies because we wouldn't see them. We might not understand cosmic structure because we'd lack examples to study. We might not even know about the cosmic microwave background's fluctuations that reveal how structure formed, because we'd have no local examples of structure to compare against the early universe's patterns. Our cosmology is shaped by our location. We're fortunate to live in a rich region of space, in a galaxy that's part of a group that's part of a supercluster, where we can see thousands of galaxies and study how the universe is put together. That accident of location, being born in a dense rather than underdense region, has enabled our understanding of the cosmos. Void dwellers, if any exist, would have a much harder time figuring out how the universe works. The isolation would be profound. The nearest significant structure in any direction would be roughly 165 million light-years away at the void's edge. Even at light speed, messages would take 165 million years to reach anything outside the void. You'd be cut off, fundamentally isolated, living in a bubble of emptiness surrounded by a universe you could only barely detect, even with the most powerful instruments imaginable. There's something both terrifying and beautiful about that isolation, isn't there? The terror of being alone in that much emptiness, the beauty of the profound silence, the dark spaces between rare points of light. It's sublime in the philosophical sense, vast enough to defeat comprehension, strange enough to provoke both fear and fascination. Edmund Burke, when he wrote about the sublime in the 18th century, argued that it required vastness, infinity, magnitude that exceeds our ability to grasp. The Boötes Void offers all of that. It's vast beyond visualization. It approaches infinity in any practical sense. 330 million light-years might as well be infinite for any being that experiences time on human scales. It has magnitude that utterly defeats our imagination. But Burke also noted that the sublime requires some obscurity, some inability to see the thing clearly, some aspect that remains mysterious. The void provides that too. Despite decades of study, despite mapping it carefully and measuring its properties, the void remains somehow obscure. We can describe it mathematically, we can plot its boundaries, but we can't really see it, can't experience it, can't make it feel real in any visceral way. It exists as numbers and maps and abstractions, never as lived experience. Immanuel Kant expanded on Burke's ideas, describing what he called the mathematical sublime, the feeling that arises when we confront quantities so large they overwhelm our faculty of imagination. We can think about 330 million light years. We can work with it mathematically, but we can't imagine it. The imagination fails, and in that failure, Kant argued, we recognize something about the limits of human cognition, about how we're finite beings trying to comprehend infinities. The void demonstrates this perfectly. We understand it intellectually. We've measured it. We know its properties. But the understanding remains purely abstract. The mind's failure to really comprehend the scale is itself meaningful. It reveals something about us and about the structure of reality we're trying to understand. There's also something sacred about emptiness in various philosophical traditions, and perhaps those traditions are worth considering as we contemplate this cosmic void. Buddhist philosophy speaks of shunyata, often translated as emptiness, but not meaning nihilistic nothingness. It refers to the emptiness of inherent existence, the recognition that things don't have fixed, permanent essences, but arise in relation to everything else. The void is empty of galaxies, yes, but it's full of potential, full of quantum fields, full of dark energy, full of space itself. It's not nothing, it's a different kind of something. Taoist philosophy celebrates emptiness as functional, as useful. The Tao Te Ching says, 30 spokes converge at the hub, but it's the emptiness that makes the wheel useful. We shape clay into a pot, but it's the emptiness inside that holds whatever we want. The void in the cosmic web might be similar, not a flaw or absence, but a necessary feature, the space that allows structure to exist at all. You can't have filaments without the spaces between them. You can't have walls without the empty rooms they define. The void is part of the pattern, not an aberration. Indigenous Australian cultures speak of the dreaming, that eternal present where ancestral beings shape the landscape and continue to exist. The dreaming includes both the formed and the formless, both presence and absence, both the land and the empty spaces within it. Creation emerges from formlessness. The void, in that sense, isn't the opposite of creation, but its complement, its partner, the formlessness from which structure emerges and into which it might eventually dissolve. Modern life has its own voids, its own empty spaces that perhaps mirror the cosmic ones. We live in an age of information overload, constant stimulation, endless content streaming into our awareness through screens and speakers and notifications. Social isolation despite being constantly connected, the paradox of modern existence, surrounded by people, bombarded with information, and yet somehow feeling alone, feeling empty, feeling like there's a void at the center of experience that no amount of content can fill. Maybe that's why the Boötes Void resonates, why it's compelling despite being nothing, why we keep coming back to study it and think about it. It mirrors something we feel, some modern condition of being surrounded yet isolated, connected yet empty. The void becomes a mirror for our own experience, projected onto cosmic scales, made literal in the structure of the universe itself. But we should be careful not to overinterpret, not to read too much human meaning into physical structures that exist regardless of what we think about them. The void isn't a metaphor, isn't a lesson, isn't trying to teach us anything. It's just a region of space where, for reasons we're still working to fully understand, galaxies are extraordinarily rare. The meaning we find in it is meaning we bring to it, patterns we impose because humans are pattern-seeking creatures who can't help but find significance in things that might just be physics following its own rules. Still, there's something undeniable about scale-collapsing meaning, about how numbers can become so large they cease to signify anything experiential. We can say 330 million light years, and we can calculate with that number, and we can compare it to other numbers and build up a mathematical understanding of what it represents. But we cannot truly imagine it, cannot make it feel real, cannot bridge the gap between abstract knowledge and lived comprehension. Perhaps that's the void's first lesson, if it has lessons at all. Some truths can only be understood, never felt. We know the void exists. We've measured it carefully. We understand its properties with reasonable precision, but we cannot comprehend it in any full sense, cannot hold its vastness in our minds as anything more than an abstraction. The knowing and the feeling remain forever separated by the immensity of the scale involved. And yet we must try. We must find ways to talk about it, to think about it, to place it in context even when context fails, because understanding the void, even understanding that we cannot fully understand it, tells us something important about the universe we inhabit. It reveals that space can be emptier than we imagined, that structure formation can produce absences as dramatic as any presence, that the cosmic web has holes in it large enough to swallow our entire conception of what galaxies should be and where they should be found. The void is vast, the void is empty, the void defeats comprehension while inviting it, and now that we've tried, and largely failed, to make its scale feel real, we can move forward into understanding how such a thing could exist at all. How does the universe build such enormous bubbles of almost nothing? What processes shape space into structures and anti-structures, into matter and emptiness, into the cosmic web and the voids within it? Those are questions we can answer, at least partially. The scale may defeat us, but the mechanisms are comprehensible, and understanding how voids form will help us understand why Boötes is so extreme, why it pushes right up against the edge of what should be possible, why its very existence tells us something important about how the universe organizes matter across the larger scales we can observe. Now we come to what might seem like a strange question. How do you build something out of nothing? Or perhaps more accurately, how does the universe create such profound emptiness in a cosmos that started out remarkably smooth and uniform? The Boötes Void exists, we've established that. We've tried to comprehend its scale, but understanding what it is and how large it is doesn't tell us how it came to be. For that, we need to go back to the beginning, not quite to the Big Bang itself, but close enough that things get genuinely strange. The early universe, shortly after the Big Bang, was remarkably smooth. Not perfectly smooth. We'll get to the imperfections in a moment because they are crucial, but smooth enough that if you could somehow have stood anywhere in the universe about 380,000 years after the Big Bang and looked around, you would have seen basically the same thing in every direction. Hot, dense plasma filling all of space, glowing with thermal radiation, with no obvious structure, no galaxies, no stars, no interesting features whatsoever, just a nearly uniform fog of matter and energy. This smoothness is visible today in something called the cosmic microwave background, or CMB. That hot plasma eventually cooled enough that atoms could form, and when that happened, the radiation that had been bouncing around between charged particles suddenly had nothing to interact with and just started travelling in straight lines. That radiation is still travelling today, stretched by cosmic expansion from visible light into microwaves, filling the entire sky with a faint glow that we can detect with radio telescopes. And when you map that glow across the whole sky, you see that it's extraordinarily uniform, the same temperature in every direction to within about 1 part in 100,000. But, and this is the crucial part, it's not perfectly uniform. There are tiny fluctuations, tiny differences in temperature from one region to another, representing tiny differences in density in the early universe. These fluctuations are small, almost absurdly small. We're talking about variations of about 18 millionths of a degree. But those tiny variations were the seeds from which all cosmic structure grew. Here's where cosmic inflation comes in, and I promise we'll keep this relatively brief because inflation is one of those topics that can get extremely technical very quickly. In the first tiny fraction of a second after the Big Bang, somewhere around 10 to the minus 36 seconds to 10 to the minus 32 seconds, which is a span of time so short that trying to visualize it is pointless. The universe underwent a period of exponential expansion. Space itself expanded faster than light could travel, driven by a field we don't fully understand, but which had the effect of smoothing out the universe while simultaneously amplifying quantum fluctuations into cosmic scale variations in density. Those quantum fluctuations, tiny random variations in energy density that existed at subatomic scales, got stretched by inflation into variations spanning millions or billions of light years. They're the reason the CMB isn't perfectly smooth. They're the seeds of all structure, and they fell into a pattern. Some regions were slightly more dense than average, some regions were slightly less dense than average, just tiny differences, but differences nonetheless. And then gravity went to work. Gravity is a remarkably simple force in terms of its basic rule. Masses attract each other. That's it. That's the whole thing. But when you apply that simple rule across billions of years, across enormous volumes of space, across countless particles all pulling on each other simultaneously, you get extraordinarily complex behavior. You get structure formation. Here's how it works. Take a region that's slightly more dense than average, just slightly, maybe 1 part in 100,000 more dense. That region has slightly more mass than surrounding regions, which means it has slightly more gravity, which means it pulls matter from surrounding regions toward itself. As matter flows in, the region becomes more dense, which increases its gravity, which pulls in more matter, which increases density further. It's a positive feedback loop. The rich get richer, gravitationally speaking. Meanwhile, the regions surrounding that overdense area are losing matter. They're becoming less dense as material flows away toward the overdensity. And as they become less dense, they have less gravity, which means they're less effective at holding on to the matter they have, which means more flows away, which makes them even less dense. Another positive feedback loop, but running in reverse. The poor get poorer. This process has been running for nearly 14 billion years, since shortly after the Big Bang. The tiny initial differences in density, those quantum fluctuations stretched to cosmic scale by inflation, have been amplified by gravity over billions of years into the dramatic structure we see today. The slightly overdense regions have become galaxy clusters and superclusters. The slightly underdense regions have become voids. Dark matter plays a crucial role here, and we need to talk about it because it's the dominant player in structure formation. Dark matter makes up about 85% of all the matter in the universe. It doesn't interact with light, hence dark, but it does interact through gravity, and gravity is what matters when you're building cosmic structure. Dark matter started clumping together first, earlier than ordinary matter, because ordinary matter was still coupled to radiation in the early universe and couldn't collapse as easily. Dark matter had no such restrictions. It just followed gravity, pulling together into clumps that would eventually become the scaffolding on which galaxies formed. So the timeline looks something like this. About 380,000 years after the Big Bang, matter and radiation decoupled. Atoms formed, the cosmic microwave background was released, and matter became free to respond to gravity without being pushed around by radiation pressure. Dark matter had already started collapsing into structures at this point. By about 100 million years after the Big Bang, the first structures were forming, dark matter halos, that would eventually host the first stars and galaxies. By about 1 billion years, galaxies were emerging, growing, beginning to organize themselves into the patterns we see today. And that process has been continuing ever since, for the last 13 billion years or so, with structure growing, evolving, matter flowing along gravitational gradients, the cosmic web becoming more pronounced with time. And the voids. The voids formed as the natural consequence of matter flowing away from underdense regions toward overdense ones. They're not being pushed apart by some repulsive force. They're being evacuated as matter drains away toward regions with stronger gravity. Imagine water flowing downhill. The valleys fill up while the hills become relatively drier. Voids are the gravitational hills, the regions matter flows away from. They expand over time, not because they're being pushed, but because there's less and less matter in them to resist the expansion of space itself. This is where computer simulations become invaluable, because we can't actually watch structure formation happen. It takes billions of years, and we've only been doing astronomy for a few thousand. But we can simulate it. We can set up a virtual universe with the right initial conditions, apply the laws of physics, and let the computer evolve it forward in time, watching what happens to matter as gravity does its work over billions of simulated years. And what these simulations show, simulations with names like the Millennium Simulation, Illustris, Eagle, is that the universe naturally develops a structure that looks remarkably like a three-dimensional spider web, or like soap bubbles packed together, or like a neural network. Take your pick of analogies. They all capture different aspects of the same basic pattern. There are filaments where galaxies cluster together in long chains. There are walls or sheets where galaxies form two-dimensional surfaces. There are nodes where multiple filaments intersect, creating dense concentrations that we call galaxy clusters. And there are voids, the bubbles in the foam, the spaces between the filaments, the empty regions where galaxies are rare. This structure is remarkably consistent across simulations. Different research groups using different codes and different assumptions all get basically the same result. The cosmic web emerges naturally from the initial conditions of the early universe plus gravity plus 13 billion years of evolution. It's not imposed from outside. It's not the result of some exotic physics. It's just gravity doing what gravity does when you give it quantum fluctuations to work with and billions of years to operate. The statistics are striking. About 80% of the universe by volume consists of voids, but those voids contain less than 10% of the matter. The vast majority of space is empty or nearly empty, while most of the matter is concentrated into relatively small volumes along the filaments and walls. The cosmic web is mostly empty space with thin threads of structure running through it, and we happen to live on one of those threads where matter is relatively concentrated. So that's how voids form in general. Matter flows away from underdense regions. Gravity amplifies small initial differences over billions of years, and you end up with a universe that's highly structured, full of dramatic contrasts between overdense filaments and underdense voids, between regions packed with galaxies and regions where galaxies are rare. But this brings us back to the Boötes Void specifically, because understanding how voids form in general doesn't explain why Boötes is so extreme. The lambda CDM model, our standard model of cosmology, the one that includes dark energy, lambda, and cold dark matter, CDM, predicts that voids should exist. It predicts their typical sizes. It predicts their typical densities. And Boötes sits right at the edge of those predictions, or possibly just beyond them, depending on exactly how you run the numbers. Statistical analysis of cosmic structure shows that voids as large and empty as Boötes are rare, but not impossible. If you survey enough of the universe, if you look at enough volumes of space, you should eventually find a few voids that are statistical outliers. The extreme cases, the ones that represent the tail end of the distribution. Boötes might be one of those. Just rare enough to be surprising, but not so rare that it couldn't happen by chance given the size of the observable universe. But there are other possibilities. Maybe the formation conditions in that particular region of space were unusual. Maybe the quantum fluctuations from inflation happened to create an especially large underdense region there. Not impossible, just unlikely. Inflation is a quantum process, and quantum processes have randomness built in. Most regions get average-sized fluctuations, but occasionally you get lucky or unlucky depending on your perspective and end up with a much larger or much smaller fluctuation than typical. Or maybe multiple smaller voids merged. Voids can grow over time, and if several adjacent voids expand and eventually connect, you could end up with one very large void that's actually the result of several smaller voids combining. This is plausible and has some support from simulations, though it's hard to prove after the fact, because once voids merge, you can't easily tell whether you're looking at one large void or several merged small ones. Or maybe there's something about the local dark matter distribution that we don't fully understand. Dark matter dominates structure formation, and if the dark matter in that region had unusual properties or an unusual distribution, it could potentially create more extreme voids than we'd expect from the standard model. This is more speculative and ventures into territory where we're limited by our incomplete understanding of what dark matter actually is and how it behaves in all circumstances. The point is, we're still investigating. We understand the general mechanisms of void formation quite well. We can simulate the cosmic web and reproduce the kinds of structures we observe. But Boötes specifically, why it's so large, why it's so empty, why it formed in that particular location, those remain open questions. We have hypotheses, we have possible explanations, but we don't have definitive answers. And maybe that's appropriate for a structure as strange as this one. Now, before we move on to exploring what few galaxies do exist inside the void, we should take a moment to recognize that the story of void formation echoes some very old human stories about creation. Not because the physics is mystical. It's not, it's perfectly comprehensible and follows well-understood laws. But because humans have always told stories about how order emerges from disorder, how structure arises from formlessness, how something comes from nothing or nearly nothing. Greek mythology begins with chaos, not chaos in our modern sense of disorder and confusion, but chaos as a primordial void, an initial emptiness. From Hesiod's Theogony, first chaos came to be, and from that emptiness, from that initial void, the ordered cosmos emerged. Gaia, earth, Tartarus, the underworld, Eros, desire, and everything else that followed. The void came first. Structure came after. Egyptian creation myths speak of Nu or Nun, the primordial waters, the formless expanse that existed before the ordered world. Not quite a void, but an undifferentiated emptiness, a state of non-being from which being emerged when the first god appeared, standing on a mound rising from the waters, bringing order to chaos. Norse mythology has Ginnungagap, that yawning void between Niflheim, the world of ice and cold, and Muspelheim, the world of fire and heat. In that gap, in that emptiness, the first beings emerged when ice and fire met and mingled, when the void became a space of creation rather than mere absence. The biblical account in Genesis describes the initial state as tohu wabohu, often translated as formless and empty, or without form and void. The emphasis is on absence of structure, absence of order, before the creative process begins and organizes the cosmos into its various parts and features. There's a common pattern across these myths. Order emerges from disorder, structure from formlessness, cosmos from chaos, and while these are religious and mythological accounts rather than scientific ones, they capture something true about how structure formation actually works. The universe did start in a more uniform state. Structure did emerge over time from tiny initial variations. Gravity did organize matter, creating dramatic contrasts between full and empty regions. The myths got the basic pattern right, even if the mechanisms they imagined were very different from gravitational collapse and dark matter dynamics. There's also a philosophical tradition, particularly in Eastern thought, that recognizes emptiness as productive, as functional, as necessary for form to exist at all. Taoist philosophy celebrates this. The Tao Te Ching, that foundational text attributed to Lao Tzu, contains a famous passage. 30 spokes converge at the hub, but it's the emptiness that makes the wheel useful. We shape clay into a pot, but it's the emptiness inside that holds whatever we want. The emphasis is on how emptiness enables function, how void space is what makes structures useful, how absence is as important as presence. Buddhist philosophy has a similar concept with shunyata, often translated as emptiness or voidness, but not meaning nihilistic nothingness. It refers to the emptiness of inherent existence, the recognition that things don't have fixed, permanent, independent essences, but arise in relationship to everything else. Everything is interconnected. Everything depends on everything else, and the void is part of that interconnection. It exists because the cosmic web exists. It's defined by its relationship to the filaments and walls. It has meaning only in the context of the larger structure. You cannot have structure without negative space. This is true in art, in design, in architecture, in music. The empty spaces define the shapes. The silences give rhythm to sound. The voids in a building are as important as the walls. They're the rooms, the spaces where life happens. A sculptor carving a statue removes material to reveal form. The statue is as much about what's been taken away as what remains. The universe works the same way in a sense. Gravity is the sculptor, matter is the material, and the cosmic web is the form that emerges when matter is redistributed according to gravitational gradients. Some regions end up dense with matter, the filaments, the walls, the galaxy clusters. Other regions end up empty. The voids, the spaces between, the regions matter flowed away from. You need both. Structure requires contrast. The web wouldn't be a web without the holes. This doesn't mean the void is intentional, of course. Gravity doesn't have intentions. Physics doesn't care about aesthetics or meaning. The universe isn't sculpting structure according to some artistic vision. It's just following mathematical laws, matter responding to forces, structure emerging from simple rules applied over vast timescales. But the pattern that emerges, this contrast between full and empty, this creation of structure through subtraction as much as addition, is reminiscent of how human artists work when they create forms from formlessness. And perhaps there's a lesson there, or at least an observation worth making. Creation often works through what you don't include as much as through what you do. The sculpture gains its form from the marble removed. The poem gains its power from the words left out. The cosmic web gains its structure from the regions where matter isn't, the voids that define the boundaries and emphasize the density of the filaments by contrast. The Boötes Void isn't a mistake or a flaw in cosmic design. There is no design, there's just physics, but if we're going to talk about patterns and structures, the void is part of the pattern. It's a necessary feature, or at least a natural consequence, of how gravity sorts matter when given quantum fluctuations as initial conditions. Gravity didn't create the void by accident. Gravity created the cosmic web, and the void is the price, or perhaps the prerequisite of structure. You can't have one without the other. So now we understand, at least in outline, how voids form. Tiny quantum fluctuations in the early universe, amplified by inflation, amplified further by billions of years of gravity pulling matter together in some regions and leaving it sparse in others. The result, a cosmic web of filaments and walls surrounding enormous bubbles of nearly empty space. And among those bubbles, occasionally, you get an extreme outlier, a void like Boötes, larger and emptier than it should be, pushing at the boundaries of what the standard model predicts, challenging our understanding while still remaining just barely within the realm of the possible. But understanding how the void formed doesn't explain everything, because the void isn't completely empty. There are galaxies inside it, not many, about 60 compared to the 2,000 that should be there. But they exist. Strange, isolated galaxies living in the most underdense environment imaginable. And those ghost galaxies, those rare inhabitants of extreme emptiness, have their own story to tell. That's where we're heading next, into the mystery of how anything survives in a place where almost nothing exists. Here's where the void gets genuinely strange, because it's not completely empty. It should be, or nearly so. That's what the statistics predict. That's what makes sense given how structure formation works. Matter flows away from underdense regions toward overdense ones, leaving voids with very few galaxies. But the Boötes Void has galaxies inside it. Not many, and they're extremely odd, but they exist. They're survivors of some kind, or perhaps latecomers, or possibly something else entirely that we haven't quite figured out yet. They're the ghost galaxies, the rare inhabitants of emptiness, and they raise more questions than they answer. Let's start with the census, because numbers matter here. Based on average galaxy densities across the universe, based on how many galaxies we typically find in a given volume of space, the Boötes Void should contain approximately 2,000 galaxies. That's the prediction. That's what normal cosmic structure would produce in that volume. The first surveys, back in the early 1980s when Kirshner and his colleagues were mapping the void, found 8 galaxies. 8, not 800, not 80. 8 scattered across a volume that should have contained thousands. And at first, there was the natural question, did we miss some? Were there more galaxies there that just happened to be too faint to detect, or that were hidden behind dust, or that for some reason didn't show up in the survey? Later surveys, using more sensitive instruments, better detection methods, deeper observations, did find more galaxies. The count has been revised upward over the decades as technology improved. Current estimates put the number at around 60 galaxies total in the void's interior. 60. That's still only about 3% of the expected population. It's not that we were missing most of them, it's that most of them simply aren't there. And those 60 galaxies aren't evenly distributed. Some cluster near the edges of the void where conditions are slightly less extreme, where they're closer to the filaments and walls where normal structure exists. Some are genuinely in the interior, in the deepest parts of the void where isolation is most profound. The distribution suggests that being in a void is marginal for galaxy formation. Galaxies can exist there, but barely, and only under specific circumstances we're still working to understand. But here's what makes these ghost galaxies fascinating. They're different, not just rare, but genuinely unusual compared to galaxies in normal environments. They have properties that set them apart, that mark them as void dwellers, that reveal something about what isolation does to galaxies over billions of years. First, they tend to be smaller, lower mass, fewer stars. This makes sense. In underdense regions where matter is sparse, you'd expect the galaxies that do form to be relatively small, simply because there's less material available to collect into galactic structures. The largest galaxies form in the densest regions where lots of matter is available. Void galaxies form where matter is scarce, so they stay relatively modest in size. Second, they're generally bluer than normal galaxies. In astronomy, colour tells you about stellar populations. Blue galaxies contain lots of hot, young, massive stars, stars that burn bright and blue but die quickly. Red galaxies contain mostly older, cooler stars, stars that have settled into long, sedate lives, having exhausted the gas supplies needed to form new generations. Blue means active star formation. Red means quiescence, the twilight years of galactic evolution. Void galaxies tend toward blue. They're actively forming stars, often at rates comparable to or even higher than similar mass galaxies in normal environments. This is surprising. It suggests they haven't run out of gas, haven't exhausted their fuel supplies, haven't entered the red and dead phase that most galaxies eventually reach. Third, their morphologies, their shapes and structures tend toward irregular or dwarf, spiral forms. They're not the grand, well-organized spirals or massive ellipticals you find in dense environments. They're smaller, messier, less symmetric. They look like galaxies that haven't been shaped by interactions with neighbors, that haven't been tidied up by the various processes that sculpt galaxies in crowded environments. Fourth, they're isolated, profoundly, almost absurdly isolated. The nearest neighbor for a typical void galaxy might be millions of light years away, distances that are enormous even by cosmic standards. For comparison, the Milky Way and Andromeda are only 2.5 million light years apart, and we're heading for a collision because we're so close. Void galaxies have neighbors at distances 5 or 10 times that, if they have nearby neighbors at all. Some are even more isolated, floating alone in darkness with the nearest significant structure tens of millions of light years distant. Fifth, they're gas-rich. They contain substantial amounts of neutral hydrogen, the raw material for star formation, that they haven't yet converted into stars. This is unusual. Most galaxies go through their gas supplies over time, converting it into stars or losing it through various processes. But void galaxies seem to have held onto their gas, preserving it, using it slowly and steadily rather than burning through it quickly. Sixth, they have lower metallicity. In astronomy, metals means any element heavier than hydrogen and helium, oxygen, carbon, nitrogen, iron, everything else. These elements are produced in stars and released when stars die, enriching the interstellar medium and eventually being incorporated into new generations of stars. Metallicity is therefore a kind of history. It tells you how many generations of stars have lived and died, recycling material. Low metallicity means fewer previous generations, less stellar processing, a more pristine composition closer to the primordial mix of hydrogen and helium-helium that emerged from the Big Bang. So void galaxies are small, blue, actively star-forming, irregularly shaped, extremely isolated, gas-rich and metal-poor. They're like living fossils, galaxies that have evolved slowly, that haven't been through the transformative events that shape most galaxies, that represent what happens when you form a galaxy and then leave it almost completely alone for billions of years. Why are they blue and actively forming stars? This turns out to be a question about what stops star formation in normal galaxies, because the answer to why void galaxies keep forming stars is basically nothing stops them. In normal environments, in galaxy groups and clusters, along the filaments where galaxies are relatively close together, several processes work to shut down star formation. These quenching mechanisms, as astronomers call them, are the reason most massive galaxies are red rather than blue, why they've stopped making new stars and settled into gentle decline. One mechanism is tidal stripping. When galaxies get close to each other, their mutual gravity creates tidal forces, the same kind of differential gravitational pull that creates ocean tides on Earth. These tidal forces can pull gas out of galaxies, stripping away the raw material needed for star formation. If you lose your gas, you can't make new stars, and your existing stars gradually age until the galaxy turns red. Another mechanism is ram pressure stripping. In galaxy clusters, space isn't quite empty. There's hot gas filling the space between galaxies, heated to millions of degrees by the cluster's gravitational potential. When a galaxy moves through this hot gas, it experiences ram pressure, like the wind resistance you feel when sticking your hand out of a moving car window. That pressure can strip gas out of the galaxy, blowing it away like leaves in a wind, removing the fuel for star formation. A third mechanism involves the central supermassive black hole that most galaxies host. When these black holes actively accrete matter, they can produce enormous amounts of energy, jets and winds that blow through the galaxy, heating gas and preventing it from cooling and collapsing to form stars. This AGN feedback, named after active galactic nuclei, is thought to be particularly important for the most massive galaxies. All of these mechanisms require either neighbors or high-density environments. Tidal stripping needs other galaxies nearby. Ram pressure stripping needs hot intracluster gas. AGN feedback is more common in massive galaxies in dense environments where black holes have plenty of material to feed on. These are processes that happen when galaxies live in crowds, when they interact and interfere with each other, when the local environment is active and dynamic. Void galaxies have none of that. They're isolated. They have no neighbors to tidally strip their gas. They're not moving through hot intracluster medium because there are no clusters in voids. Their black holes, if they have them, are probably small and quiet, lacking the material to become active. Nothing interferes with their star formation. Nothing removes their gas. They just keep going, slowly and steadily converting their gas into stars at a pace they can sustain for billions of years. They're like hermits living alone in the wilderness, self-sufficient, unchanged by the social pressures and interactions that shape those living in cities. and that isolation preserves them in a state that normal galaxies grow out of, actively star-forming, gas-rich blue, representing what galaxies look like when left undisturbed by their environment. But this raises an uncomfortable question. How did they form at all? And perhaps more puzzling, why are they still there? The standard story of structure formation says that matter flows away from underdense regions toward overdense ones. That's how voids empty out. So any galaxy that formed in what would become the void should have been pulled toward the edges, dragged along by the same gravitational currents that removed most of the matter from the void's interior. Over billions of years, you'd expect the void to become even emptier as whatever galaxies did form early on migrated toward denser regions. And yet, 60 galaxies remain, scattered through the void, some near the edges, but some genuinely in the deep interior, apparently stable in their positions, not being evacuated despite billions of years of structure evolution. There are several possible explanations, none entirely satisfying, all requiring special circumstances or unlikely timing. Maybe these galaxies formed very early, before the void fully evacuated, and they managed to hold onto enough dark matter to resist the outward flow. Maybe they're located at local dark matter overdensities within the void, small concentrations of dark matter that provide just enough gravitational anchoring to keep a galaxy in place even as the surrounding region empties out. Maybe they formed from gas that was falling inward toward denser regions but got caught somehow, trapped in stable orbits or slowed by friction, and ended up making galaxies in the void rather than continuing outward. Maybe they're tidal dwarf galaxies, small galaxies created when larger galaxies outside the void had close encounters that flung material into the void, material that then collapsed to form these strange isolated systems. Maybe they survived by being just dense enough, just massive enough, just stubborn enough that their own self-gravity held them together against the forces trying to pull them apart or push them away. The threshold for survival in a void might be very sharp. Slightly less massive and you get torn apart, slightly more massive and you survive. The 60 galaxies we see might represent the lucky few that were just above that threshold. Computer simulations struggle to reproduce void galaxies accurately. You can make voids in simulations easily enough. Just start with the right initial conditions and let gravity do its work. But getting galaxies to form and survive inside those simulations voids, in the right numbers and with the right properties, turns out to be difficult. The simulations want to evacuate the voids more completely than observations show. They want to drag galaxies toward the edges or prevent them from forming at all. This suggests we're missing something. Either the initial conditions were different than we assume, maybe the quantum fluctuations in those particular regions had properties that favor void galaxy survival. Or maybe there's some physics we don't fully understand, some process that affects how galaxies form in extremely underdense environments, some subtlety in how dark matter behaves in voids, some effect we haven't accounted for. The ghost galaxies challenge our models. Their existence is uncomfortable, theoretically speaking. They shouldn't be there, or they should be much rarer than they are, or they should have different properties than they do. The fact that they exist at all, in the numbers we observe, with the characteristics we measure, tells us that our understanding of structure formation in extreme environments is incomplete. And there's something poetic about that incompleteness, isn't there? The void is defined by absence, by what's not there, and even that absence isn't complete. Even in the emptiest place we've found, life persists, or at least galactic life, if we're being whimsical about it. The ghost galaxies are survivors, holdouts, stubborn existences in a place that should be barren. Throughout human mythology, isolation and exile carry deep meaning. Prometheus, The Greek Titan who gave fire to humans was chained to a rock in eternal punishment, isolated from the community of gods. Cain, in biblical tradition, was marked and sent to wander, cut off from human society as punishment for killing his brother. Buddhist hungry ghosts, or pretas, wander alone, isolated by insatiable desire that prevents them from finding peace or community. Norse mythology has Loki bound in punishment until Ragnarok, isolated beneath the earth, venom dripping on his face, while he waits for the end of the world. Exile and isolation are punishment in these stories. They're the cost of transgression, the price of wrongdoing, being cut off from community, from connection, from the normal structures of social existence. This is portrayed as torment, as suffering, as one of the worst fates imaginable. But there's another tradition, quieter and perhaps less dramatic, that sees isolation differently. The Desert Fathers of early Christianity withdrew from society to find enlightenment through solitude. Hermits and ascetics across various traditions have chosen isolation as a path to truth, believing that withdrawal from social complexity allows for deeper understanding. Monks in remote monasteries, sages in mountain caves, mystics in wilderness retreats, all choosing isolation not as punishment but as opportunity. In this framing, the Void Galaxies aren't exiles but hermits. They're not being punished. They simply exist in a different mode, living lives incomprehensible to crowded galaxies like our Milky Way, maintaining their inner light despite outer darkness. No distractions, no gravitational encounters, no tidal forces pulling them apart, no environmental pressure shutting down their star formation. Pure existence without entanglement, without the complications that come from having neighbours. Is this tragedy or wisdom? Are the ghost galaxies fortunate or cursed? They'll never merge with neighbours, never collide, never be shaped by the kinds of interactions that define galactic evolution in normal environments. They'll simply exist, alone, making stars in the silence, evolving according to their own internal rhythms, rather than being pushed and pulled by external forces. There's something both beautiful and terrible about that kind of existence. Beautiful because it's pristine, undisturbed, authentic. Terrible because it's lonely, isolated, fundamentally separate from the normal flow of cosmic evolution. And perhaps that reflects our modern condition too. 21st century life comes with its own voids, its own paradoxes of isolation. We're more connected than ever. Instant communication across the planet, social media linking billions of people, information flowing constantly. And yet loneliness is epidemic. Social isolation despite constant connection. The paradox of being surrounded by people, bombarded with interactions, and still feeling fundamentally alone. Void galaxies mirror that. They exist in a universe full of structure, full of other galaxies, full of cosmic activity, but they might as well be in a different universe for all the contact they have with that structure. The nearest neighbour is too far away for any meaningful interaction. They're connected to the cosmic web only in the most abstract sense. They're part of the same universe, subject to the same physical laws, but functionally isolated from the dynamic processes that shape most galaxies. Does loneliness destroy or preserve? The Void Galaxies suggest both. Neither. It depends on perspective. They've been preserved in a sense. They've maintained their star formation, kept their gas, stayed blue and active, while their cousins in dense environments turned red and quiescent. But they've also been limited. They've remained small, unable to grow through mergers, stuck at modest masses because there's no additional material to accrete. Their isolation has shaped them in ways both protective and constraining. And they continue. They persist. They make stars in the darkness, convert gas to light, maintain their existence against the emptiness surrounding them. Not thriving, perhaps, but not dead either. Just continuing, generation after generation of stars, lighting small corners of vast darkness, existing because they can, because the physics allows it, because sometimes survival is enough. The ghost galaxies are the void's inhabitants. Few, strange, isolated, inexplicable according to our best theories. They live lives we can study but not truly understand, lives shaped by an environment so different from our own cosmic neighbourhood that the normal rules seem not to apply. They're survivors of something, or witnesses to something, or accidents of cosmic geography that manage to persist despite all the forces working against their existence. And they remind us that even absence isn't absolute, that even in the emptiest place we've found, something remains. The void isn't void, it's mostly empty, profoundly underdense, as close to nothing as cosmic structure gets. But it's not nothing. It has its ghosts, its rare inhabitants, its stubborn existences that refuse to conform to theoretical expectations. They're there, strange and isolated and actively star-forming in the silence, making light in the darkness, existing alone, and somehow that makes the void even more mysterious, even more strange than if it were completely empty, because complete emptiness we could understand. But this sparse scattering of galaxies that shouldn't exist, surviving where survival should be impossible, this we're still working to explain. So now we come to the theories, the attempts to explain why the Boötes Void exists, why it's so large, why it's so empty. And here's where things get interesting, in that slightly frustrating way that science often does, because we have several plausible explanations, none of them definitively proven, all of them reasonable, and the truth might be some combination of all of them, or something we haven't thought of yet. Scientists don't like admitting this, but sometimes the honest answer to why does this happen is, we're not entirely sure. But here are some educated guesses. Let's start with the most boring theory, which is also possibly the most likely. The statistical argument goes like this. The universe is really, really big. Bigger than we can observe, actually. The observable universe has an edge only because light from farther away hasn't had time to reach us yet. Not because the universe ends there. And when you have something that's truly enormous, with countless regions and volumes and structures, occasionally you're going to get statistical outliers, rare events that are technically possible but highly unlikely. The Boötes Void might just be one of those. Think of it this way. If you flip a coin 10 times, getting all heads would be weird but not impossibly so. It happens about once in every 1,024 attempts. Rare, but within the realm of expected statistical variation. The Boötes Void might be the cosmic equivalent of flipping all heads. Rare enough to be surprising. Common enough that in a universe this large, it probably had to happen somewhere. The lambda CDM model, our standard cosmological model that includes dark energy, lambda, and cold dark matter, CDM, predicts how structure should form from the initial quantum fluctuations in the early universe. When you run the calculations, when you simulate structure formation millions of times with slightly different starting conditions, you get a distribution of void sizes and densities. Most voids cluster around average values, but the distribution has tails, rare extreme cases that are statistically possible even if uncommon. Boötes sits out on one of those tails. It's at the edge of what the model predicts should be possible, or maybe just barely beyond that edge depending on exactly how you calculate the probabilities. The numbers suggest that in an observable universe containing hundreds of billions of galaxies, organized into millions of voids, you might expect to find a handful of voids as extreme as Boötes. Maybe even 2 or 3. We found one. That could just be luck. Statistical variation doing what statistical variation does. The cosmological principle tells us that the universe should be homogeneous at large enough scales. If you zoom out far enough, every region should look pretty much like every other region. But large enough scales means roughly 500 million light-years or larger. Boötes is about 330 million light-years across, which is right at the threshold where you'd still expect to see significant variation. It's large, yes, but not quite so large that finding one extreme void becomes impossible. So the statistical argument is basically, it's rare, but the universe is big, so rare things happen sometimes. Not a particularly satisfying explanation emotionally, but often correct. The universe doesn't owe us dramatic explanations. Sometimes things just happen because the probabilities allow them to, and we notice them because they're unusual. But that's the boring theory. Let's talk about some more interesting ones. The dark energy hypothesis starts with a mystery wrapped in a mystery, which is appropriate for a discussion about voids. Dark energy is this strange component that makes up about 68% of the universe's total energy density, and we don't really understand what it is. We know it exists because we can measure its effects. The universe's expansion is accelerating, space is being created faster and faster over time, and dark energy is the name we give to whatever's driving that acceleration. But as for what dark energy actually is, what it's made of, how it works at a fundamental level, we're still figuring that out. Most models treat dark energy as a cosmological constant, a property of space itself that's the same everywhere and doesn't change over time. But it doesn't have to be constant. There are alternative models called quintessence, where dark energy is a dynamic field that can vary in strength from place to place or evolve over time. And if dark energy varies by location, if it's stronger in some regions than others, that could potentially create larger voids. Here's the logic. Dark energy has negative pressure, which creates a kind of repulsive gravity that pushes things apart. If dark energy were stronger in certain regions, those regions would expand faster than average, matter would flow away more quickly, the void would evacuate more thoroughly. You could end up with voids that are larger and emptier than you'd expect if dark energy were perfectly uniform. There's also an interesting question about whether voids themselves affect dark energy. Some models suggest what's called a void phenomenon, the idea that expansion might work slightly differently in underdense regions compared to overdense ones. Space in voids, being less cluttered with matter, less constrained by gravitational interactions, might expand slightly faster than space in filaments and walls. It's a subtle effect, hard to measure, but if it's real, it could explain why some voids grow larger than predictions suggest they should. The measurements on this are inconclusive. Some studies find hints that voids might expand slightly faster than average space. Other studies find no significant difference. The effect, if it exists, is small enough that it's hard to separate from measurement uncertainties and other complicating factors. So the dark energy hypothesis remains plausible but unproven, an interesting possibility that might explain Boötes, or might not. Now let's get really speculative with the inflation bubble theory. Remember cosmic inflation, that brief period about 10 to the minus 36 seconds after the Big Bang, when the universe underwent exponential expansion? Most inflation models predict that quantum fluctuations during inflation should produce a scale invariant power spectrum, meaning fluctuations of all sizes should have similar amplitudes, at least within certain ranges. Small fluctuations, large fluctuations, medium fluctuations, they should all follow the same statistical pattern. But that's just the simplest models. More complex inflation models allow for non-uniform inflation, for variations in how inflation proceeded in different regions. Some models even involve bubble nucleation, where inflation starts and stops at different times in different places, creating a kind of foamy structure at the largest scales. If inflation wasn't perfectly uniform, if it had quirks and variations, you could potentially end up with unusually large, underdense regions that would become unusually large voids. The Boötes Void could be, in this scenario, a scar from inflation, a region where the quantum fluctuations happen to create an especially large, underdense patch, or where inflation works slightly differently, leaving behind conditions that would eventually produce an extreme void. It's highly speculative. We can't observe inflation directly. We can only see its consequences in the cosmic microwave background and in large-scale structure, but it's not impossible. There are hints in the data that inflation might not have been perfectly uniform. The cosmic microwave background has some anomalies, features that don't quite match the simplest predictions. There's something called the axis of evil, an unexpected alignment of the largest scale fluctuations that probably doesn't deserve such a dramatic name, but got it anyway. There are cold spots, regions of the CMB that are slightly colder than they should be. That might be connected to supervoids or might indicate something odd about inflation. Could Boötes be related to these anomalies? Maybe. The void is in a different part of the sky from the main CMB cold spot, so they're probably not directly connected, but they could share a common cause in unusual inflation behavior. This ventures into territory where we're connecting speculative explanations to uncertain measurements and hoping something meaningful emerges, which is how science sometimes works, but also how you can fool yourself into seeing patterns that aren't really there. Some inflation models also connect to multiverse ideas, the notion that our universe is one bubble in an eternally inflating larger structure, and maybe Boötes represents a bubble within a bubble, a nested structure where inflation happened at multiple scales. This is fun to think about, and makes for good theoretical physics papers, but it's also almost impossible to test observationally, which means it might be untestable in principle, which means it might not really be science in the traditional sense. But I mention it, because if you're looking for exotic explanations for an extreme structure, this is about as exotic as you can get, while still remaining within the bounds of theories that physicists take somewhat seriously. Finally, let's talk about edge phenomena. What happens at the boundary of the void where emptiness transitions into structure? Because voids aren't static. They're not just sitting there unchanging. They're dynamic structures embedded in an expanding universe, with matter flowing along gravitational gradients, with subtle currents and patterns that we're only beginning to map in detail. The void's boundary isn't sharp. There's no wall, no fence, no clear line where inside becomes outside. Instead, there's a transition zone where galaxy density gradually increases as you move from the interior toward the filaments and walls that surround the void. This transition region is interesting because it's where you can see the dynamics most clearly. Matter flowing, galaxies moving, the void and the web interacting. One question astronomers have been trying to answer is, are galaxies flowing away from the void, or are they flowing toward the denser regions around it? It sounds like the same thing, but it's not quite. If galaxies are being pushed by some repulsive force originating in the void, that would tell you something different than if they are being pulled by attractive gravity from the dense regions surrounding it. The physics is different, the implications are different. The answer appears to be mostly pulled, with maybe a slight component of push from faster expansion in the void, but the measurements are difficult and the uncertainties are large. Galaxies have what are called peculiar velocities, motion beyond the Hubble expansion, motion due to gravitational interactions with surrounding structure. Measuring these velocities requires very precise distance measurements, and at the distances we're talking about, precision is hard to achieve. What we can say is that the flow patterns are complex. Matter moves along the filaments. It drains from the void's interior toward the boundary. It creates currents and streams and subtle gravitational rivers that shape how structure evolves. The void isn't just sitting there empty. It's actively participating in the larger dynamics of structure formation, albeit in a negative way, in the sense that it's defined by what's flowing out of it rather than into it. And the void is expanding probably, though maybe not much faster than the rest of the universe. Space everywhere is expanding due to dark energy. In voids, where there's less matter to slow things down gravitationally, expansion might proceed slightly more freely. But it's a gentle effect, not some dramatic runaway process. The void grows slowly, matter continues to avoid it, and over billions of years it becomes slightly larger and slightly emptier. The process is ongoing but gradual, operating on timescales that make billions of years feel short. The edge is where the void meets the web, where nothing transitions into something, where the empty spaces give way to structure. It's a zone of transformation, of change, of boundaries that exist not as lines but as gradations. And studying these edges might ultimately tell us more about the void than studying its interior, because edges are where things happen, where dynamics are visible, where the contrast reveals the pattern. So those are the theories. Statistical outlier, variable dark energy, inflation anomalies, edge dynamics, some combination of all of them, or something we haven't thought of yet because we're still learning how structure formation works at the larger scales, still developing the tools to measure the subtle effects that might explain extreme structures. Each theory is plausible, none's confirmed. The void keeps its secrets by being exactly what it is, enormous, empty, just barely possible according to our best models. It challenges our understanding without quite breaking it. It raises questions without quite demanding revolutionary new physics to answer them. It's strange, but maybe not strange enough to require strange explanations. Or maybe we're missing something important. Some crucial piece of physics that would make the void seem obvious in retrospect rather than puzzling. Throughout human history, we've been fascinated by liminal spaces, the thresholds, the boundaries, the in-between places where one thing becomes another. The anthropologist Arnold van Gennep studied rites of passage and identified what he called liminal periods, times when someone is betwixt and between, no longer who they were, but not yet who they'll become. Victor Turner expanded on this, describing liminality as a state of ambiguity, of being on the threshold, of existing in the margins between defined categories. Doorways are liminal, twilight is liminal, borders between countries, shorelines between land and sea, the moment between sleeping and waking, all liminal spaces where normal rules become fluid, where transformation happens, where magic was once thought to work because the usual boundaries were thin or absent. The void's edge is the ultimate liminal space in that sense. It's the boundary between structure and emptiness, between something and nothing, between the organized cosmic web and the formless expanse of the void's interior. It's where galaxies thin out but don't quite disappear, where the normal rules of structure formation start to fail but haven't completely broken down. It's threshold space on a cosmic scale. Celtic mythology speaks of thin places, locations where the veil between worlds is gossamer, where one realm touches another, where crossing between becomes possible. Mountains, certain coastlines, stone circles, places of power and possibility where the boundaries that normally separate become permeable. The edge of the void is a thin place in that metaphorical sense. It's where the cosmic web touches the cosmic emptiness, where matter meets absence, where normal structure fades into something else. Not literally magical, but strange in ways that invite wonder. Every culture has border mythology. The Greeks had the river Styx, the boundary between the world of the living and the underworld, a river you could cross but only with proper payment and at the end of life. Norse mythology had Bifrost, the rainbow bridge connecting Midgard to Asgard, a boundary between human and divine realms. Egyptian mythology described the Duat, the realm between life and death that souls travel through during their judgment. Chinese tradition spoke of the Yellow Springs, a boundary realm beneath the earth. Borders are powerful in mythology because they represent transition, transformation, the movement from one state to another. They're places of danger and possibility, where the rules change, where you leave behind what you knew and enter something uncertain. The void's boundary fits this archetype even if it's just physics rather than mythology. It's where one kind of space becomes another kind of space, where the rules of structure formation shift, where galaxies go from common to rare, where the universe demonstrates that it has different modes of being. Crossing that boundary, if you could somehow travel through it, would mean leaving behind everything familiar about cosmic structure and entering a realm of isolation and emptiness, so profound it's almost incomprehensible. There's also a philosophical question about boundaries worth considering. What makes a boundary real? The void doesn't have a wall. There's no fence marking where inside becomes outside. Just a gradual decrease in galaxy density, a transition zone that spans millions of light years. And yet we draw a boundary, we say, this is the void's edge. We treat it as if there's a definite inside and outside, even though nature doesn't work with such clean distinctions. Buddhist philosophy would note that this separation is a mental construct. Form is emptiness. Emptiness is form, says the Heart Sutra. The void and the web aren't truly separate. They're part of one continuous system, one unified structure where what we call empty and what we call full are just different densities along a spectrum. The boundary exists because we need boundaries to understand things, to categorize, to make sense of patterns. But nature itself has no boundaries, just gradations, transitions, continuous flows of matter and energy responding to forces. We impose the distinction between void and web because our minds work through distinctions, through categories, through drawing lines between things. But the universe doesn't know it has voids. It doesn't recognize boundaries. It just has matter distributed in various densities according to gravity and initial conditions. And we're the ones who look at that distribution and say, this region is notably empty. Let's call it a void and study it as a distinct structure. Which doesn't make the void less real. The emptiness is genuine, measurable, significant, but it reminds us that how we understand structure depends on how we choose to define and bound it, on where we decide edges exist in a system that's fundamentally continuous. The theories multiply, but certainty remains elusive. Perhaps that's appropriate. The void isn't meant to be simple. It challenges our models, tests our predictions, sits uncomfortably at the edge of what our best theories can explain. The edge of the void becomes the edge of our understanding, that liminal space where knowledge fades into speculation, where measurements give way to hypotheses, where we must make peace with not knowing for certain. And maybe that's not a failure, but a feature. Science isn't about having all the answers immediately. It's about asking better questions, gathering more data, refining theories, and remaining comfortable with uncertainty while we work toward understanding. The void is teaching us that lesson on the largest scales we can observe, showing us that even after decades of study, even with sophisticated instruments and powerful simulations, some things remain mysterious, not because we're not trying hard enough, but because they're genuinely at the limits of what we can currently explain. The void sits there, enormous and empty, waiting for better theories, better data, better understanding. And in the meantime, it does what it does best. Nothing. Just existing. Just being profoundly empty. Just challenging us to explain how nothing became so dramatically much nothing that it demands an explanation at all. Now we arrive at a question that sounds simple but turns out to be surprisingly slippery. What is nothing? What does it mean when we say the Boötes Void is empty? Because here's where physics gets genuinely strange, where our everyday intuitions about emptiness completely fail, where the universe reveals that nothing is actually quite complicated. Classical physics, the physics of Newton, of everyday experience, of objects moving through space according to comprehensible rules, treats a vacuum as simply empty space, a region with no matter, no particles, no stuff. You remove all the air from a container, seal it up, and you've got a vacuum. Nothing inside. Empty. Done. Quantum physics looks at that same situation and says, not quite. According to quantum field theory, which is our best description of how the universe works at small scales, there's no such thing as truly empty space. Fields permeate all of space. Electromagnetic fields, electron fields, quark fields, the Higgs field, all the various quantum fields that underlie reality. These fields are everywhere, always, filling every cubic centimetre of space with their presence. You can't remove them. They're fundamental to how the universe is constructed. And these fields are never quite still. Even in their lowest energy state, even in what we'd call a vacuum, they fluctuate. They have what's called zero-point energy, the minimum possible energy, which turns out to not be zero. The Heisenberg uncertainty principle, one of the foundational ideas of quantum mechanics, tells us that energy and time have an inherent uncertainty relationship. You can write it as delta E times delta T greater than or equal to h bar over 2, which is a fancy way of saying that for very brief moments, energy can appear out of nowhere as long as it disappears again quickly enough. The result is that the vacuum seethes with activity. Virtual particles constantly pop into existence, matter-antimatter pairs appearing out of the quantum foam, existing for absurdly brief moments before annihilating and vanishing again. We're talking about timescales of 10 to the minus 21 seconds, far too brief to observe directly. These virtual particles are called virtual precisely because they can't be isolated and studied individually. They're quantum fluctuations that only exist in the context of the uncertainty principle allowing them. But they're not purely theoretical. They have measurable effects. The Casimir effect, discovered in 1948, shows that the quantum vacuum creates pressure between metal plates placed very close together. The vacuum between the plates has slightly different properties than the vacuum outside them, because certain wavelengths of virtual particles can't fit in the gap, and that difference in quantum fluctuation creates a tiny but measurable attractive force. The plates get pushed together by nothing, by the weight of quantum emptiness. There's also the Lamb shift, a tiny difference in the energy levels of hydrogen atoms that can only be explained by accounting for how virtual photons, fluctuations in the electromagnetic field, affect the electron's behavior. The vacuum isn't empty. It's full of quantum activity, of fields doing field things, of fluctuations that have real consequences, even if the particles involved are too fleeting to pin down. So when we say the Boötes Void is empty, we're already starting from a place where empty means something different than everyday intuition suggests. The void isn't empty of quantum fields. It's not empty of virtual particles. It's not empty in any absolute sense. It's just empty of galaxies, empty of significant concentrations of ordinary matter, empty in the sense that if you were somehow floating there, you'd find far fewer stars and galaxies than you would in a normal region of space. But it gets stranger, because the vacuum also has weight. Dark energy is the name we give to whatever's causing the universe's expansion to accelerate. We've known since 1998 that the expansion isn't just continuing, it's speeding up, with space being created faster and faster over time. Something is driving that acceleration, and we call it dark energy because we don't know what it is, and dark is astronomy's default prefix for mysterious. The leading explanation is that dark energy is a property of space itself, sometimes called the cosmological constant. Einstein originally introduced this constant in his equations to make the universe static. He thought the universe should be eternal and unchanging, so he added a term to balance gravity's attractive pull. Then Edwin Hubble discovered that the universe is expanding, and Einstein reportedly called the cosmological constant his biggest blunder and removed it. Except it turns out he was right the first time, sort of. The constant exists. Space does have energy density. It's just that instead of making the universe static, it makes it accelerate. The cosmological constant is real. It's everywhere. And it has a value of approximately 6 times 10 to the minus 10 joules per cubic meter. That sounds tiny, and it is for any small volume, but space is vast. The universe contains an enormous amount of space. When you add up all that tiny energy density across all those cubic meters, you get something significant. About 68% of the universe's total energy density comes from dark energy. It's the dominant component of reality, more important than ordinary matter, more important than dark matter, more important than radiation. The vacuum weighs more than anything else. And here's what's fascinating about dark energy in the context of voids. It has negative pressure. Positive pressure pushes things apart locally but attracts gravitationally. Negative pressure, which is weird and non-intuitive, creates repulsive gravity. It pushes rather than pulls. And that negative pressure is what drives cosmic acceleration. In regions filled with matter, gravity from that matter dominates and holds things together. Galaxies stay in clusters, clusters form superclusters. Structure persists despite the expansion of space. But in voids, where matter is sparse, dark energy dominates more completely. There's less gravitational attraction to counter the repulsive effect of dark energy. The ratio shifts. Same dark energy density, much less matter. So dark energy's influence becomes proportionally stronger. This might mean that voids expand slightly faster than average space. Not dramatically, not in some runaway process that makes them grow without bound, but slightly. The emptiness enables the acceleration. The nothing weighs something, and that weight is negative, and negative weight pushes outward. The void isn't empty of dark energy. It's full of it, and that fullness is part of what makes it empty of matter, or at least part of what keeps it empty once matter has drained away. Though we should be careful here because the evidence for voids expanding faster is tentative at best. Some measurements suggest it, some don't. The effect, if it exists, is subtle enough that it's hard to separate from other factors. But the principle is clear. Dark energy makes the void more void-like, emphasizes its emptiness, ensures that matter continues to avoid regions that are already underdense. The nothing weighs something. That's a strange sentence to write, but it's true. The emptiest places in the universe are full of dark energy, and that dark energy has measurable effects on how space behaves, how it expands, how it maintains its emptiness over billions of years. Now let's talk about something called the CMB cold spot, because it connects to voids in interesting and not entirely understood ways. In 2004, the WMAP satellite, which was mapping the cosmic microwave background with unprecedented precision, detected an anomaly. A region of the sky about 5 to 10 degrees across, where the CMB temperature was about 70 microkelvins colder than average. That might not sound like much, 70 millionths of a degree, but the CMB is supposed to be extraordinarily uniform. Temperature variations exist, yes, because the early universe had density variations that eventually grew into structure. But those variations are tiny, usually only about 18 microkelvins. The cold spot is several times larger than typical fluctuations, and the probability of it occurring by random chance in a standard cosmological model is very low, around 0.2%. Depending on exactly how you calculate it. So what causes it? One possibility is that it's just a statistical fluke, a rare fluctuation that happened to appear in that particular patch of sky. Another possibility is that there's an error in how we've removed foreground contamination, signals from our own galaxy and local sources that we need to subtract to see the pure CMB. But another intriguing possibility is that the cold spot is caused by a supervoid. The integrated Sachs-Wolfe effect describes how photons from the CMB can lose energy as they pass through voids. When a photon enters a void, it climbs out of a gravitational potential well. Space is less dense in the void, so there's less gravitational attraction pulling on it. That takes energy. When the photon exits the void billions of years later, it falls into the denser regions surrounding the void, which should give the energy back. But if the void is expanding during the photon's transit, and remember, the universe is expanding, so voids are growing, then the gravitational potential has changed. The well the photon climbs out of is deeper than the well it falls into on the other side. The photon loses more energy than it gains, ending up slightly redshifted, slightly cooler than it would have been otherwise. The void leaves a shadow on the CMB, a cold spot created not by conditions in the early universe, but by photons passing through an underdense region during their 13.8 billion year journey to Earth. This is a real effect. We've measured it with other voids, seen the subtle temperature decrements that large underdense regions create in the CMB. But the math doesn't quite work for explaining the entire CMB cold spot. Surveys have found a supervoid in that direction, the Eridanus supervoid, about 2 billion light-years away, which is quite large. But even accounting for that void, we can only explain part of the temperature anomaly. There's still something odd about the cold spot that we don't fully understand. Could the Boötes Void create a similar effect? Probably, though it's too far from the main cold spot to be directly connected. The principle is the same. Voids affect light passing through them. Even though they're nearly empty, even though they're defined by absence, they have measurable effects on radiation that crosses them. The void is detectable by its absence. It leaves an imprint on the cosmic microwave background, not through what it contains, but through what it lacks. And this gets at something fundamental. The void isn't nothing in any meaningful sense. It affects things. It has properties. It can be studied, measured, characterized. It's empty of galaxies, but full of space, full of quantum fields, full of dark energy, full of subtle gravitational currents that shape how photons move and how structure evolves. The emptiness is a kind of presence. Modern surveys are mapping voids systematically now. Projects like DESI, the Dark Energy Spectroscopic Instrument, and the Sloan Digital Sky Survey have built up catalogues of thousands of voids, characterizing their sizes, shapes, and densities. The Boötes Void remains the largest and most underdense, but we now understand it in context. It's part of a population, the most extreme member of a class of structures that are fundamental to cosmic architecture. The James Webb Space Telescope, launched in 2021, can detect faint galaxies that previous instruments missed. When pointed at void regions, it confirms what we suspected. Those rare void galaxies are indeed weird. Blue, isolated, actively star-forming, exactly as predicted. The observations match the theory, which is satisfying in the way that scientific confirmation always is. We thought this should be true. We built better instruments, we looked, and yes, there they are. Strange as expected. The Euclid Space Telescope, launched in 2023 by the European Space Agency, is creating an extraordinarily detailed three-dimensional map of cosmic structure. It will map positions of billions of galaxies, trace the cosmic web in unprecedented detail, and measure properties of voids with precision we've never had before. We'll be able to track how void densities change, measure expansion rates more accurately, detect subtle effects that current data can only hint at. The Vera Rubin Observatory, coming online in Chile, will scan the entire visible southern sky every few nights, creating a time-lapse movie of the universe. It will detect faint structures, track how voids evolve, catch transient events that might reveal dynamics we've missed with previous instruments. The nothing becomes measurable. We're building a science of emptiness, developing tools specifically designed to study what isn't there. And as we measure more carefully, the void becomes more complex rather than less. Every answer raises new questions. Every measurement reveals new subtleties. The void isn't simple absence. It's a rich, complicated structure with properties we're still learning to characterize, with dynamics we're still learning to model, with mysteries that persist despite decades of increasingly sophisticated observations. Western philosophy has long struggled with the concept of nothing. The idea that something could come from nothing troubled Greek philosophers. Parmenides famously declared that nothing cannot be, that non-being is incoherent, that something has always existed because nothing can't exist, and therefore can't be the origin of anything. Aristotle argued that nature abhors a vacuum, that empty space was impossible in principle because space itself was a property of objects rather than an independent thing. Medieval scholastic philosophers debated whether God could create a true void. If God is omnipotent, could he create absolutely empty space? Or would that be logically impossible, a contradiction like a square circle? Thomas Aquinas and others wrote extensive treatises trying to resolve this question, and they were right to be confused. Nothing is genuinely hard to define coherently. Modern physics confirms that they were onto something. Nothing, as we typically understand it, is incoherent. Even empty space is something. It has fields, properties, energy density. True absolute nothingness doesn't exist in our universe, at least not as far as we can tell. The closest we get to nothing, the vacuum, voids, regions far from matter, is still full of quantum activity and dark energy. Buddhist philosophy approaches emptiness differently. Shunyata, often translated as emptiness or voidness, doesn't mean non-existence. It means the emptiness of inherent independent existence. Everything arises in relation to everything else. Nothing has a fixed, permanent essence. The void isn't empty in the sense of containing literally nothing. It's empty of galaxies because conditions don't favour galaxy formation there. Empty in a relational rather than absolute sense. This feels closer to how physics actually describes voids. The void is empty of galaxies but full of space, empty of matter but full of fields, empty in relation to the cosmic web but not empty in any absolute sense. Form and emptiness aren't opposites. They're different aspects of the same system, different ways of describing how matter and energy are distributed across the universe. There's a theological tradition called the via negativa or apophatic theology that tries to describe God by what God is not rather than what God is. Pseudo-Dionysius the Areopagite wrote about the divine dark approaching truth through negation, through removing false concepts rather than adding positive descriptions. God is not limited, not bounded, not temporal, defining through absence rather than presence. The void invites a similar approach. We understand it by what it's not full of galaxies, not dense, not typical. And by stripping away those things, by focusing on what's absent, we arrive at something like understanding. The void as meditation object, the emptiness that teaches by being empty. And here in the 21st century, we have our own relationship with emptiness that the void might reflect. We live in an age of constant information, endless stimulus, perpetual noise. Notifications buzz, screens glow, content streams continuously into our awareness. And yet, or perhaps because of this, we crave emptiness. Digital detox, minimalism, Marie Kondo telling us to keep only what sparks joy and remove the rest. Meditation apps that promise 8 minutes of mental silence. Why do we seek absence? Because presence can be overwhelming, because constant stimulation exhausts, because sometimes the way to clarity is through subtraction, through creating space, through allowing emptiness rather than filling every moment with activity, and every surface with objects, and every silence with sound. The void becomes an aspiration in that context. Clear space, clear mind, clear schedule. The cosmic void as metaphor for the kind of mental and emotional space we're desperately trying to create in lives that feel too full, too cluttered, too relentlessly occupied. Maybe we need our own personal voids. Empty time, quiet rooms, blank pages, moments where nothing happens, and that's exactly right. The Boötes Void teaches us that nothing is complicated. It's not absence, but a different kind of presence. It's not empty, but differently full. Quantum fields, dark energy, rare galaxies. The void contains more nothing than we ever imagined possible. Even in the emptiest place in the observable universe, something remains. True nothingness doesn't exist. And maybe, just maybe, that's a comfort. The universe resists absolute emptiness, even where galaxies are nearly absent, where isolation is most profound, where conditions are most hostile to structure, something persists. Space itself, fields energy, the possibility of existence even in the least likely places. The void isn't nothing, and neither are the empty spaces in our own lives, the pauses, the silences, the blank spots on the calendar. They're just differently full, waiting for us to recognize what remains when we stop filling every moment with something. We've arrived at the final stretch of our journey into emptiness, and it's time to ask, so what? What does the Boötes Void mean for us, for our understanding of the universe, for the future of cosmic structure? Why should we care about an enormous bubble of nearly nothing 700 million light-years away? These are fair questions, and they have answers that range from the purely scientific to the quietly philosophical. Let's start with the present moment, or as close to present as astronomy gets, which means observations from the 2020s, our current golden age of cosmic surveys. We live in a remarkable time for studying structure. The James Webb Space Telescope, launched in late 2021, provides the deepest infrared views of the universe we've ever achieved. It can detect galaxies that were previously too faint to see, peer through dust that blocked older instruments, and capture details that would have been impossible just a decade ago. When JWST has been pointed at void regions, and yes, astronomers do waste perfectly good observing time on places where there's supposedly nothing to see, because sometimes nothing is interesting, it confirms what we've been suspecting about void galaxies. They're real, they're measurable, they're weird. Blue, isolated, actively star-forming, exactly as the theories predicted. There's something satisfying about confirmation, about seeing that your understanding wasn't completely off base, even if plenty of mysteries remain. Then there's DESI, the Dark Energy Spectroscopic Instrument, which has one of those names that sounds vaguely ominous but just describes what it does. DESI is mounted on a telescope in Arizona and is systematically mapping millions of galaxies in 3 dimensions, creating the most detailed picture of cosmic structure we've ever had. It measures redshifts for thousands of galaxies per night, building up a 3-dimensional map of how matter is distributed across enormous volumes of space. The void catalogue is expanding rapidly. We now know of thousands of voids, ranging from relatively small bubbles just tens of millions of light-years across, to enormous structures rivaling Boötes in size. We can study them statistically, see how their properties vary, understand what's typical and what's extreme. The Boötes Void still stands out. It's still the largest and most underdense of the large voids, but we now see it in context rather than as an isolated anomaly. The Euclid telescope, launched by the European Space Agency in 2023, adds another layer to this mapping effort. It's designed specifically to study dark energy and dark matter by mapping billions of galaxies with extraordinary precision. Euclid will trace the 3-dimensional structure of the universe across cosmic time, showing not just where galaxies are now, but how structure has evolved over billions of years. It will measure void properties more precisely than ever before, potentially detecting subtle effects like expansion rate variations that current instruments can only hint at. And coming soon, or relatively soon by telescope construction standards, which operate on geological timescales, is the Vera Rubin Observatory in Chile. Once it's fully operational, it will scan the entire visible southern sky every few nights, creating a time-lapse movie of the universe. Most of the focus will be on things that change, supernovae, asteroids, variable stars, but it will also provide unprecedented data on large-scale structure. It will detect faint galaxies in voids, track how structure evolves even over the few years of the survey, catch subtle changes that might reveal dynamics we've been missing. The void is becoming less mysterious through observation, in the sense that we're characterizing its properties with ever greater precision, but it's also becoming more complex. Each answer raises new questions. Each measurement reveals new subtleties. That's how science often works. You rarely solve a problem completely. You just develop better questions. Now let's talk about the future. Not our future as observers, but the void's future, and by extension the future of all cosmic structure. Because we know how this story ends, at least in broad outline, and it's both fascinating and slightly melancholy. The universe's expansion is accelerating. Dark energy is driving galaxies apart at ever-increasing rates. This process will continue as far as we can tell for the rest of time, which is a very long time indeed, possibly infinite, depending on exactly how you define time in an ever-expanding universe. The timeline looks something like this. In about 100 billion years, most star formation will have ended. Galaxies will have exhausted their gas supplies, converted what they can into stars, and the era of creating new stars will be mostly over. There will still be stars burning, small, dim red dwarfs that can survive for trillions of years. but new ones will stop appearing. By about 1 trillion years from now, the last conventional stars will have died. The universe will be populated by stellar remnants, white dwarfs, neutron stars, black holes, and the occasional brown dwarf still glowing faintly from residual heat. The night sky, from anywhere, will be dark in ways we can barely imagine. By 100 trillion years, even the white dwarfs will have cooled to black dwarfs, cold dark cinders that no longer emit detectable light. Neutron stars will have cooled. The universe will be dark and cold, illuminated only by the occasional burst of radiation when something falls into a black hole, which will be increasingly rare as matter spreads out. Eventually, and we're talking timescales so long that the numbers become meaningless, but physicists write them down anyway, even the black holes will evaporate through Hawking radiation, and then there will be nothing but cold, dark matter, neutrinos flying through empty space, and whatever dark energy is, doing whatever dark energy does. But long before that final heat death, something else will happen. Galaxy clusters will become isolated. The local group, our small collection of galaxies including the Milky Way and Andromeda and their satellites, will merge into one large galaxy over the next few billion years. That's normal. That's gravity doing its work on gravitationally bound systems. But then that merged galaxy will find itself increasingly alone. Dark energy drives galaxies apart. On small scales, within galaxy clusters, gravity is strong enough to overcome this. Clusters stay together, held by their own gravity even as the space between clusters expands. But the expansion is relentless. Over hundreds of billions of years, clusters that aren't gravitationally bound to our local group will drift beyond our cosmic horizon, the distance beyond which light can no longer reach us because space is expanding too fast. Our observable universe will shrink. Not physically, our galaxy will still be there, its stars will still shine, until they die, but observationally. The number of galaxies we can see will decrease. The cosmic web will fade. Eventually, our descendants, if any exist, will live in a universe where only our local merged galaxy is visible. Everything else will have been carried away by expansion, redshifted out of visibility, lost beyond the horizon. And what will remain? Mostly void. The universe becomes, given enough time, mostly empty space with rare islands of matter, separated by distances too large to ever cross, too large for light to bridge, too large for any information or influence to travel. The Boötes Void is a preview of this future. This is what wins in the end, not through destruction, not through some catastrophic event, but through drift. Emptiness wins by patience, by the slow, inexorable expansion of space, by time scales so vast they make billions of years feel like moments. It's a strange kind of fate. The universe doesn't end with a bang or a crunch. It just becomes increasingly empty, increasingly dark, increasingly isolated. And in that far future, the distinction between void and web will become meaningless, because everything will be void, more or less. The structure we see today, filaments, walls, clusters, the rich tapestry of cosmic organization, is temporary. It's a brief phase in cosmic history where matter is concentrated enough to be interesting, where structure persists, where observers like us can exist and study it. So why do voids matter? Beyond the immediate scientific interest, beyond the puzzle of explaining how they form, and why some are so extreme, why should we care about these enormous bubbles of nearly nothing? First, because they're laboratories. Voids are natural experiments in extreme environments. They're places where dark energy dominates more completely than in normal regions, where you can study how cosmic expansion works when there's minimal gravitational interference. They're where galaxies evolve in isolation, showing us what happens to galactic systems when you remove all the environmental effects. No mergers, no tidal stripping, no ram pressure, just a galaxy doing its own thing for billions of years. Second, because they're sensitive tests of cosmological models. The lambda CDM model makes specific predictions about void distributions, sizes, and densities. Finding voids that are larger or emptier than predicted challenges those models, forces refinements, reveals where our understanding might be incomplete. Boötes, sitting at the edge of what theory comfortably allows, is exactly the kind of structure that pushes our models and helps us improve them. Alternative theories of gravity, modifications to general relativity that some physicists propose to explain dark energy or dark matter without invoking new physics, make different predictions about void properties than standard cosmology. Some modified gravity theories predict slightly different void sizes, or different expansion rates, or different relationships between void properties and surrounding structure. By studying voids carefully, we can test these alternatives, constrain what's possible, rule out theories that don't match observations. Third, because voids reveal the universe's large-scale architecture. You can't understand the cosmic web by only studying the filaments. You need to understand the holes too, the empty spaces that define the structure's shape and evolution. Voids are as fundamental to cosmic structure as the dense regions are. They're the negative space that makes the positive space comprehensible, the emptiness that gives meaning to the fullness. And there's a fourth reason, more philosophical than scientific. Voids challenge our assumptions about what's normal. We live in a relatively dense region of space in a galaxy cluster, surrounded by other galaxies. That shapes our intuitions about what the universe is like. But by volume, the universe is mostly void. Most of space is empty or nearly empty. The dense regions where we happen to live are the exception, not the rule. Understanding voids means understanding that our perspective is biased, that what seems normal to us is actually unusual from a cosmic perspective. Which brings us to an interesting question. What if Earth were in a void? It's a thought experiment, but a revealing one. Imagine if our solar system, our galaxy, existed not in the local group at the edge of the Virgo supercluster, but inside something like the Boötes Void. How would that change our astronomy, our understanding of the universe, our place in the cosmos? Well, the night sky would be profoundly different. We'd still see stars, the Milky Way would still exist, stars would still shine, our immediate stellar neighbourhood would look more or less the same. But beyond our galaxy, there would be almost nothing. No Andromeda visible as a faint smudge, no Triangulum galaxy, no Magellanic clouds. The nearest galaxy might be millions of light years away, far too faint to see without powerful telescopes. Would we have discovered that other galaxies exist? Eventually, probably, with good enough instruments. But it would have happened much later in our astronomical development. The realization that the universe extends far beyond our own galaxy might have been delayed by decades or centuries. Would we have discovered the Big Bang? This is trickier. The cosmic microwave background would still exist. It's everywhere, a relic of the early universe that fills all of space. But would we have correctly interpreted it? Much of our understanding of cosmology comes from seeing how structure has evolved, how galaxies cluster, how the cosmic web organizes itself. Without visible examples of structure, without the Hubble flow of galaxies to measure, would we have developed the same cosmological models? Maybe, maybe not. Astronomy would certainly have developed differently, with different emphasis, different timelines for discoveries. We might have focused more on stellar physics, on our galaxy's internal structure, on local phenomena, and paid less attention to cosmology simply because there would be less to see cosmologically. And we might not have realized how unusual our situation was. If void-dwelling astronomers develop cosmology, they might assume the universe is mostly empty, because that's what they observe locally. They'd be right about their neighborhood, but wrong about the universe as a whole. Location matters for knowledge, where you observe from shapes what you can discover and how easily you can discover it. The mediocrity principle in cosmology suggests we should assume we're typical observers in typical locations, because assuming you're special is usually a good way to fool yourself, and by that principle, we're fortunate. Most matter in the universe is in filaments and walls, not in voids. Most galaxies exist in relatively dense environments. We're on the outskirts of a cluster, which isn't the densest possible environment, but certainly isn't a void. We're ordinary, cosmologically speaking, and that ordinariness has enabled our understanding. Void dwellers would be cosmologically unfortunate, rare observers in rare locations, isolated by their environment, limited in what they could discover about cosmic structure. They'd understand their local region perfectly well, but the larger universe would be mostly invisible to them, a kind of cosmic loneliness that extends to knowledge itself, to the ability to see and understand the broader context they're embedded in. So why are we fascinated by the void? What is it about cosmic emptiness that captures imagination, that keeps astronomers studying it, that makes it compelling despite being defined by absence? There's some psychology here worth examining. Humans are drawn to mysteries, to things we don't fully understand, to problems that resist easy solutions. The unexplained has power over us. It draws our attention, demands explanation, won't let go until we've figured it out. The void is mysterious not because we have no explanations, but because we have several explanations and none quite feels complete. That tension between knowing and not knowing is cognitively engaging in ways that simple ignorance or complete understanding aren't. But there's also something about emptiness specifically that resonates with us. The sublime, terror and beauty combined in contemplation of something vast requires both magnitude and obscurity. The void offers both. It's large enough to frighten if you think about it properly, strange enough to fascinate, empty enough to remain somewhat obscure even after decades of study. You can measure it but not experience it, know it but not comprehend it. That gap between knowledge and feeling creates a particular kind of wonder. And perhaps we're drawn to voids because they're the last truly mysterious spaces in a world that's been thoroughly mapped and measured. Earth has been charted, the oceans have been plumbed, the atmosphere is monitored constantly. Space still holds mystery, still offers the possibility of encountering the genuinely unknown. The void represents that possibility, a place so different from our experience that studying it feels like exploring an alien realm, despite being made of the same space and subject to the same physics as everywhere else. Modern life has its own voids, its own empty spaces. That might be why cosmic emptiness resonates. We're surrounded, yet alone. Connected, yet isolated. Bombarded with information, yet somehow feeling empty. The 21st century paradox. More of everything except meaning, contact, genuine connection. We fill our lives constantly, pack our schedules, scroll endlessly, consume content without pause, and somehow still feel that something's missing. The void mirrors that. It's empty, despite being in a universe full of matter. It's isolated, despite being surrounded by structure. It exists in a cosmos teeming with galaxies, yet contains almost none. That parallels our experience closely enough that contemplating cosmic emptiness might be a way of contemplating personal emptiness, of projecting our psychological states onto the universe's architecture. Or maybe we're drawn to the void because it represents what we've lost. Stillness, silence, space to simply exist, without constant demands on our attention. The void is 330 million light-years of room to breathe. It's empty in ways we rarely experience anymore, quiet in ways that feel increasingly precious. It doesn't demand anything, it just exists, vast and undisturbed, maintaining its emptiness with perfect indifference to everything beyond its boundaries. But we should be careful about reading too much human meaning into physical structures. The void isn't a metaphor. It's not trying to teach us anything. It's just a region of space where galaxies are rare because matter flowed away billions of years ago following gravitational gradients. The meaning we find in it is meaning we bring to it, patterns we impose because we're meaning-making creatures who can't help but find significance in things that might just be physics being physics. And yet, there's something undeniable about how emptiness teaches us to see fullness more clearly. The void reminds us that absence is information, that negative space defines positive space, that silence makes sound meaningful, that darkness makes light visible, that rest makes work possible. The pause between heartbeats, the void in the cosmic web, everything in relation, nothing existing independently. This is ancient wisdom confirmed by modern science. Buddhist emptiness teaching that form and emptiness are inseparable, that you can't have one without the other, that they're different aspects of a unified system. The cosmic web and its voids aren't separate things. They're one structure, one pattern, one system where matter and absence define each other mutually. We live in an age that fears emptiness. Horror vacui, the fear of empty space, manifests as constant filling, schedules packed, walls covered, silence broken, every moment occupied. But the void suggests another way. Not everything needs to be full. Not every space needs to be occupied. Not every moment needs activity. Sometimes empty is enough. Sometimes nothing is exactly what's needed. The Boötes Void will never be visited, never crossed, never truly known beyond our measurements and models. It exists too far away, remains too empty to offer destinations even if we could travel there. But maybe that's appropriate. Maybe some things are meant to remain mysterious, not because we're ignorant, but because mystery itself has value, because the universe is richer with unsolved puzzles, because knowing everything would be less interesting than knowing most things and wondering about the rest. The void is empty. That emptiness is real, measurable, significant, and somehow that emptiness speaks to us across 700 million light-years, across all the structure between here and there, reminding us that nothing is complicated, that absence is presence, that sometimes the most interesting thing about the universe is what isn't there. So we've arrived at the end of our journey into emptiness, though of course the void itself continues. Indifferent to whether we're paying attention or not, let's take a moment to look back at where we've been, because sometimes the best way to understand something is to trace the path that brought you there. We started in 1981 with confused astronomers staring at data that didn't make sense. They'd pointed their telescopes at a region of space expecting to chart thousands of galaxies and found almost nothing. Not instrumental failure, not bad luck, just genuine, profound emptiness, where emptiness shouldn't be. A bubble 330 million light-years across containing roughly 3% of the galaxies it should have held. The discovery was strange enough that they had to check and recheck, had to convince themselves, and then the broader astronomical community that what they'd found was real. And it was real. Still is, actually. The void hasn't gone anywhere, hasn't filled in with galaxies during the decades we've been studying it. It's still there, enormous and profoundly underdense, sitting about 700 million light-years away in the direction of the constellation Boötes, just waiting patiently for us to understand it. What have we learned in the 40-plus years since that discovery? Quite a bit, actually. We've learned that the void formed naturally through gravity-sorting matter over billions of years, over dense regions pulling matter toward them, under dense regions becoming emptier as material drained away. We've learned that it's part of a larger pattern, the cosmic web of filaments and walls and nodes with voids as the bubbles between. We've learned that while Boötes is extreme, it's not unique, just the largest and emptiest of a population of thousands of voids that help define how the universe organizes itself at the largest scales. We've learned about the ghost galaxies, those 60 or so strange isolated systems that somehow survive inside the void despite all the forces working against their existence, blue, actively star-forming, gas-rich, preserved in a state that normal galaxies grow out of, living fossils showing us what isolation does to galactic evolution. We've explored theories about why the void is so extreme. Statistical fluke, possibly. Variable dark energy, maybe. Unusual inflation conditions, perhaps. Subtle dynamics at the edges where matter flows along gravitational currents. The theories are plausible, but none are proven, which is honest and appropriate for a structure this strange. And we've discovered that nothing is surprisingly complicated. The void isn't empty in any absolute sense. It's full of quantum fields, seething with virtual particles, permeated by dark energy that gives the vacuum weight and negative pressure. Even the emptiest place in the observable universe still contains something. True nothingness doesn't exist, at least not in our cosmos. But some things remain unknown. We don't know for certain why Boötes is quite so large, quite so empty, quite so statistically extreme. We don't fully understand how the ghost galaxies formed and survived. We're still refining our measurements, still improving our models, still asking questions that we don't quite have answers for. The mystery hasn't been completely solved, and maybe that's fitting. Some puzzles resist final solutions, not because we're not smart enough, but because they're genuinely at the edges of what we can currently explain. There's weight to this knowledge, isn't there? We've quantified nothing, we've mapped absence, we've studied emptiness so thoroughly that it's become a subfield of astronomy, with its own specialists and conferences and technical papers. We've made a science of the void which is uniquely human. No other species that we know of contemplates cosmic voids, measures them, builds theories about them. This curiosity about what isn't there, this drive to understand even the empty places, might be our defining characteristic. And we live with this knowledge now, carry it with us. The void exists whether we think about it or not. It's part of our cosmic neighborhood, part of the architecture we're embedded in. On clear nights, if you look toward Boötes, that kite-shaped constellation visible from spring through fall, you're looking in the direction of the void. You can't see it, obviously, because that's the whole point. But it's there, 700 million light-years deep, a bubble of almost nothing vast enough to contain thousands of galaxies, if only there were galaxies there to contain. Knowing it's there changes something subtle about how you see the sky. Those dark patches between stars that you always assumed were just normal darkness. Well, they are mostly. But beyond them, deeper, past all the visible stars and past Andromeda and past the edge of our local supercluster, there's a different kind of darkness. The cosmic dark, the true emptiness of a void, the silence of space that's even more silent than usual, because there's so little there to make any metaphorical noise. The void isn't hiding anything sinister, despite what our title might have suggested. No aliens lurking in the darkness, no parallel universes leaking through, no cosmic monsters waiting in the deep. Just emptiness. Profound mathematical real emptiness that formed through natural processes and persists through cosmic expansion. And somehow, that's stranger than any fiction we could invent, that the universe builds these enormous bubbles of almost nothing as a normal part of how structure forms, that absence can be as dramatic as presence, that nothing can be significant enough to study for decades. So let's end where endings should be, with an invitation to rest, to drift, to let these ideas settle gently into sleep. Imagine floating there, in the void, surrounded by darkness in every direction. The nearest galaxy is 165 million light-years away, just a faint smudge of light against infinite black. No constellations to guide you, no Milky Way band stretching overhead, just scattered points of light, rare and distant, and silence. Absolute cosmic silence. No solar wind, no stellar radiation, no gravitational waves rippling past. Just you, suspended in the nothing, drifting through emptiness so vast that it makes even cosmic distances feel inadequate. Would it be lonely? Probably. Would it be peaceful? Perhaps. Would it be terrifying or calming or both or neither? Hard to say, but maybe the void is the universe's invitation to stillness, to rest in the darkness between stars, to drift and dream and dissolve into the quiet. A place where nothing happens, and that's exactly right. A pause in the cosmic symphony, a rest between the notes, a breath before the next phrase begins. The void is empty, the void is full, the void is nothing and everything and something in between. It's there, waiting, patient, indifferent, enormous. It doesn't need our understanding. It doesn't care whether we study it or ignore it. It just exists, doing what voids do best, nothing at all. Something strange is hiding in the Boötes Void. Maybe it's nothing. Maybe that's everything. Thank you for journeying with me tonight into this cosmic mystery, into this exploration of emptiness and what it means when nothing becomes something worth understanding. Whether you're drifting towards sleep or simply letting these ideas settle into contemplation, I'm grateful you chose to spend this time among the stars, or in this case, among the profound absence of them. If this journey resonated with you, if it helped you find that particular kind of peace that comes from contemplating things larger than ourselves, I'd be forever grateful if you tap the like and subscribe buttons and if you'd share it with others who might appreciate a gentle astronomical voyage into the unknown. And if you'd like to continue exploring the cosmos together, there are more journeys waiting, more mysteries to investigate, more wonders to discover, more quiet corners of the universe to contemplate as you drift toward rest. This is the Sleepy Astronomer, wishing you clear skies, peaceful dreams, and the comforting knowledge that even in the emptiest places something remains. May you find your own stillness in the spaces between, your own rest in the cosmic dark. Until next time, sleep well among the stars.